week I can.
It's a teamwork here.
Keep pushing shit that you're explaining. But we're not gonna see anyone knows something else. Oh, this is exciting to me.
No, you definitely. You definitely do it.
But it's probably a good thing if he doesn't.
You so. So you want to have a little introduction, or can I just share the first line?
Yeah, no, share the first one, that's pretty. Oh, shit, okay, no, 1:15, we said.
Yeah. But at least we are set.
You're amazing,
No,
and it's recording, or is it?
it's recording and it's sharing.
So
It's
what,
time-
so
I
the
remember.
recording from yesterday, is that automatically?
No, because I think it has to be go through Grant.
Okay, so Grant knows,
Yeah.
and he'll put it
Yeah,
on,
he will put
okay.
it on. It also
Because I
now-
don't think it stays on very long,
I think it's
like they delete it eventually,
I don't know.
but.
But
I mean,
they are
I
saying,
think-
I think he knows,
Okay,
but
but he's back on Saturday.
Yeah.
Right?
Yep.
Maybe it's for yesterday. Or whatever. For filling it in. I don't know if you have a very strong, I think, budget. Okay.
Okay. We just, yeah, I want to say.
Normally it's great. Yeah, if they can build something custom, it's cheaper, that's a good idea. Yeah, yeah. Yeah. Yeah, I think the less you have in the field. Because they. Maybe they understand what they're doing.
Wow.
We've still got 15 minutes. 30 minutes.
But it's the longer. Based on your scale of.
You're gonna like box, no, you're. No, he's gonna have to stretch his skin and. He's very friendly. Or you experience. Okay. Good, we have some participants online. Let's see who's there. Good. Okay. And to introduce the second day of the symposium. But I got Stephanie to chair the session, Stephanie and Patrick, and over to you, Steph.
Thank you, everybody. Starting our, dedicated people to consider a nature hall on a Thursday afternoon before a long weekend. So thank you, everybody. For being
Is okay, and for those at home, you only get half the brownie points because that doesn't count at all. I know this is a serious science seminar, but I had to share a story about Sue since it's also a celebration of Sue as well. So I think in high school, at some point, I said to my mother, I want to study volcanoes. And my mom just shook her head because where in South Africa are there volcanoes and how the heck do you make money off of volcanoes? And then at some point in my undergrad, I met Sue and I told her this, expecting her to shake her head. And she said, sure, we'll make a plan. And I think that has characterized my relationship with Sue, of just like, you can bring her the craziest ideas and she's always good and up for anything. And so that I think has made a huge impact in my life. I think it's kept me in geophysics. I think I would have gone somewhere else otherwise, even though I did branch out in my PhD. But another memory that came to mind was the first time I really got to know Sue was in our honors year. And I'm not going to mention what year that was because it was a very long time ago. And it was a small group of, and there was me and another honors student, and then 2 demonstrators who hit it off well and had lots of fun on our field trip. And at some point, somebody bought a monkey, a toy monkey. And only who would have been patient enough to put up with us and that blimmin' monkey who was called Mojo. And Mojo got in every photo ever taken everywhere. And I don't know too many other lecturers who would be patient enough to put up with that.
Where's Mojo?
Steve gave it to his mom to wash, and he was never seen again. So I don't know what happened to Mojo. He even got taken to Hawaii to see the lavas. And we swore that one day we would start a geophysics company called GeoMojo. So Sue, you'll have to be a founding member of that company. So thank you for all that you've done, because I think all of your students know that it's not just the science side of things that you help with, but actually the emotional support. Because I've always said you get a master's and a PhD for the emotional turmoil that it causes you. So thank you for many times for putting up with my emotional turmoil. But the first speaker today is Janine, and Janine is also one of Sue's students. And I was with Janine at the council for a short time. And Janine was my mentor. And I think we sat there every week, both just shaking our heads, saying how hard a PhD was. So Janine, I think you've also been part of that journey. So please come up. You'll be talking about the work that you've done in the Bushveld complex. I think nobody has looked as thoroughly at the data as Janine has. And nobody is as keen on Fletcher as Joe and Sue and you. So yes, I think all is running smoothly. Are we unmuted? Yes. Thank you. You know how to find very loads of things.
Yeah, at the bottom, yeah.
Perfect.
I'll try to talk loudly, but it's difficult. Thank you very much for the invitation, Sue. It's really an honor for me. And I also just want to give a shout out. Okay, whatever. Shout out to you, the passion you have for students. I mean, Patrick and I often talk about it. It's just amazing. The willingness, the things that you like, Stephanie said, the things you do for students, you're always passionate and friendly and everything. And thank you also for being my supervisor in this. Okay, so today I'm going to talk, this still comes from my PhD, which took a long time to finish, but in the end I got there. So yeah, so it's coming from there. We've continued to work on it. So it's not, everything is not that old. So I normally hate this slide. Patrick will know if there's a slide I hate is the outline slide, because I find it's pointless. But in this case, because it's a bit of a long talk, I thought should give you an idea of when you can start to know the end is in sight. So I'm going to look at three sections. First, just a very short overview of modeling, geophysical modeling of the Bushveld over the years. And then the bulk of the talk will be about modeling the deeper material under the Bushveld, and then why we think these results are important. So let's look at the modeling. So everybody who's ever looked at geophysics will know, or of the Bushveld will know these figures. Originally, the Bushveld was thought to be like a low polar. And then when the gravity got collected, and in the first gravity in the 1950s and so on, then they saw that you can't model the gravity data with a model like this. And Cousins came up with these 2 separate intrusions. And that stayed sort of around for a few decades. And then Ray Durham, no. Really? And people also, Andre Duplessis and Dr. Kleewacht, and so they came up with a different model where they did show that it was actually, you can also model the data as dipping sheets, not these separate intrusions, but the dipping sheets with nothing with no bushveld in between. And then this remained sort of the model for another few decades. And then Sue and Grant Cawthorne started to say, but you can model the bushveld as continuous if you take into account that you have some depression of the mower due to the density of the bushveld in the upper crust, that the mower will be depressed. And then when the SASSI data that Ray spoke about yesterday became available, it was actually found that yes, the crust is thicker under the bushveld complex, and you can model it as a continuous feature or body. So then I did a 3D model of the whole bushveld complex. I did forward modeling using magnetics to mostly look at the shadow stuff, and then gravity, and also including MOA from the SASSI data. And then the constraints I had with the geological maps, petrophysical properties from publications and that we've done at the council, and also boral data that Anglo Platinum made available. And then also just borals, deep borals like the bead coral and so on, that's been available and published over the bushveld, and a few seismic lines. At one year, the Sikukuni line, and this one north of Pretoria, and there was a published one from JCI that Jeff Campbell published. So these were my constraints. And I'm not going to go into detail into this. This is not what the talk is about, but just to see how we got to the deep stuff. So I modeled, there's like two models basically showing the western lobe. This is the thickness of the Rustenburg layered suite. So the western lobe is pretty stable, not stable, but it's like not very complicated. You have just the thick where you have the comes close to the surface, and then it sort of levels out. This is the depth to the top of the Rustenburg layered suite. But in the eastern lobe, you have more things happening. You have the Denelton Dome, and there's more granite and granophyre at the top here. So it's a bit more complicated. What I also modeled was this Mokopane feeder, which was already modeled in 1976, I think, by Maurits van der Merwe. But also you have to have a deep feeder there to model that big anomaly there. And then also along the southeastern lobe, you can model quite a deep feeder here to fit the anomaly. At the same time, Carol Finn from the USGS was my supervisor. She did inversion modeling of the northern lobe. I just focused on the central part of the bushveld. And she also found, she also had to model the Mokopane feeder, and also found some deeper stuff or thicker dense material in the Tabazimbi Murchison lineament, which is a major feature here. Also in my model, I needed to add some dense material in this part of the Tabazimbi lineament, the Droogkloof thrust, and she also had to model it in her model, which we then interpreted as also sort of feeder zones, that the Tabazimbi Murchison lineament is an important zone for the bushveld complex. And this is just also to the top of the Rustenburg layered suite. But then where we come to what I'm going to talk about today is that I've found that even taking into account the mower and everything, I still needed to add some dense material somewhere in the crust, and I put it at the boundary here based on some of the shear wave velocity work that Aldrich Kaswani did, to fit the gravity properly. If I don't have it there, it's sort of, I can't fit the gravity perfectly. you can say I can just shift that, but it doesn't work like, it didn't work like that. In certain areas, you needed more thick material. In other areas, you didn't really need thick material. So made us think maybe we are dealing here with potential staging chambers under the Bushveld complex. So that's what we then went to investigate further. So this is basically the first part of the talk. So now we're looking at the deep stuff. So we made the area bigger to include also the Mullapoort Farms complex. There's also the Moshaneng complex. They're both similar ages to the Bushveld complex. So that's important to take them into account as well. And then the data we had for the seismic demography data was the SASSI data, which was collected in the late 90s. And it was sort of in total, data were collected at 79 stations, broadband stations. And then in the from 2013 to 2018, there's also a network of autonomously recording seismographs. And we use the data from Botswana. They call it NARS Botswana. And they had 21 stations that collected data there. And the availability of this data is really very important for this study. So if I can show you things that we've learned from these data sets. First of all, the crustal thickness. This is actually the average of 5 crustal thickness models that's been published. There's been more, but these were the ones that were available when I did this. So it shows, as you can see, this is the depth to the Moho. So under especially the western part of the Bushveld complex in the northern lobe, near where you have the Tabazimbi Murchison lineament, the crust is definitely quite a bit thicker than in the surrounding areas. Also, as you move westward, you can see under the far western lobe, it is also a bit thicker, and it's sort of also a little bit thicker towards the Mullapoort Farms complex. But mostly this is the thickest part. Another thing that we got from the data is this VP over VS. It gives you an indication of the composition of the crust, and apparently 1.77 is considered sort of the average value for crust, and the higher the value is, or the ratio is, the more mafic the crust becomes. So if you look at this once again, here under the northern and western lobe and extending to the eastern lobe, we see lots of the crust is more mafic, which makes sense because you have the Bushveld complex in the crust, but in general, the crust is more mafic. Also here under the Mullapoort Farms complex. And then the one group, they looked at something called the Moho sharpness, which has to do with the phase amplitude of the P2S conversions at the Moho. And they normalize it to say, compared to the rest of the data in the study area, how sharp is the Moho. I might be explaining it wrong, but in any case, the lower the value is, the more diffuse the crust mantle transition is. So here in the south, this means the high values means you have sharp Moho, but under the Bushveld, we have diffuse transition from the crust to the mantle. And interestingly enough, a lot here under the eastern lobe, but once again in this area and extending to the western lobe. Unfortunately, we didn't have this data. So it ends here. Okay, so now we have 3 things. We have a diffuse crust mantle transition, mafic material, and the thick crust. One way to visualize it together is to look at to make a ternary image. And I thought, just to clarify, because sometimes you look at a ternary image, you're not sure what you look at. So I'll explain how we got to this. So where the Moho is diffuse and the crust is thick and mafic, I want dark colors. So the lower value show here. So the average of the apparent VP over BS, we know that high values actually mean more mafic material. So to be able to have low values being more mafic, I hope I'm making, I don't confuse you. We have just to take inverse of that. So now these values are the most mafic values. So I just want to say, if you see purple arrows and things, it's for you. The Mo sharpness, okay, this is fine because we want the lower values to indicate where we have diffuse Mo, and this is the case. And then the depth to the Mo, the larger values, which is negative, the biggest negative values must also be the lowest. So what we do then is plot the apparent VP over VS, the inverse of that in the red band. So the darker values means more mafic. And the green, the more diffuse Mo means it's darker, and the deeper Mo is darker. Okay, I hope that makes sense. So in this area where we have this dense mafic material, deep Mo, and the diffuse transition, you can see it's very dark. It extends a little bit to either side of this big anomaly here. There's not so much over the Muller-Farms complex, but it's still sort of more similar color than in the surrounding areas of the areas surrounding the Bushveld complex. Okay, so then let me just take you through then the process that we went through, or I went through. So what we see, to summarize the seismic data, we see weak P2S conversions under the Bushveld complex, which means that there is a diffuse crust mantle transition, which means that there must be a lower velocity contrast over the Mo than in the areas surrounding the Bushveld complex. And what can explain this? Why would it be? One proposal often is this magmatic underplating. So you have denser material under there. The other one is that you have a mafic lower crust. And so the question is, how mafic is the lower crust in any case away from the Bushveld complex? Is it different under the Bushveld complex from the areas around it? So the data there is that what we see, they did a denser array of seismometers that of a broadband seismic array, whatever study, around Kimberley, where there's no Bushveld. And they found there that the lower crust has an intermediate composition. And then also Ray and them use tremors to do a seismic refraction survey with the Witwatersrand. And they had a lower crust that's made of felsic granulate that they saw there. So in general, we don't expect the lower crust. If you use velocities and so on from these studies, the lower crust composition is density is about 2860 kilogram per cubic meter in that region. But yeah, so that is not what we see. We see this in our model, this mafic material. So now to test this, can you model the gravity data with this mafic material at in the lower crust? So instead, I showed it. I found it in the forward modeling, but then we did inversion, sort of as a test, and we had two models to start to test. This one is the first starter model is very oversimplified. So you just have the cover, then you have the Rustenburg layered suite of about 8 kilometers, just Archean crust with one density, and the upper mantle. This boundary is from the seismic receiver function data. And in the modeling, in the inversion, this boundary under the depth of the Rustenburg layered suite was allowed to vary unconstrained. Also, the upper mantle here is a bit more dense than in other areas because of it's depleted in magnesium, so you have effectively more iron content, which will give it higher density. Okay, so and then the second model, we added a dense lower crust. up to 24 kilometers. And in this model, the depth of the Rustenburg Lake Suite was limited to 10 kilometers. It couldn't go deeper than 10 kilometers, except where there's maybe feeders. 10 kilometers is conservative because we know from modeling, from seismic data and so on, that it's not really thicker than 7-8 kilometers, but we to go to 10 kilometers. And this upper boundary of the dense lower crust was allowed to vary unconstrained. The reason for using this density is that using a lower density, like for less mafic material, ended up in a very, very thick, unrealistically thick lower crust. Also, I must say that in my model, I used a higher density for that mafic material at the bottom. But remember now, here in this model, it can be a combination of the lower crust and then the extra material in there. That will then, so that's why I think this density can be defended. So first of all, the results when we have no dense lower crust. If you look at the inverted Rustenburg Lake Suite thickness, if you look at the values here at the bottom, it's really unrealistic. I mean, even here where it's sort of green, yellowy colors, it's like 22, 25 kilometers. It's really not realistic. Also, the extent is bigger, although, you know, we don't say this is definitely Rustenburg Lake Suite. It can be anything other else that's dense, but still the thickness is really unrealistic. So then for the second one, this is the thickness of the Rustenburg Lake Suite. The values or the thicknesses are much more realistic, like what we expect. It mustn't, the purpose of this was not to model the upper crust in detail. So it looks a little bit like there's no bushveld here, but or thin bushveld. Even in my model, it's quite thin in this area. But the point is just that we don't have that excessively thick bushveld. So it's much more realistic. But now if we look at the thickness of the lower crust, the dense lower crust, it becomes interesting. This area where we saw that dark anomaly on the ternary map, you see there's the thickest crust, thickest lower crust, or the dense lower crust. It coincides here with the Tabazimbi Murchison lineament. Now I'll just show you some profiles. So you can see from south to north, here we go over there. So this is the Rustenburg Lake Suite up to around there. And you can see the deeper moa, which means there was the isostatic adjustment. There is and then if we look at the next profile, this one here, there's the southern feeder here. And you can see the crust is a little bit thicker over there, coinciding there. And then up here also we have the Tabazimbi Murchison lineament. The crust is in that area a bit thicker. The stuff to the north here is not bushveld, it's probably greenstones or something, but we're not interested in that. And then if you look at the east-west, here we have the Molopro Farms complex here. We have quite thick lower crust. And then under the far western lobe, it goes up a bit, and under the this is where this thing is in the way. This is the southern margin of the Tabazimbi Murchison lineament. So there again we have thicker crust. And then this, oh yeah, this one, sorry. And this one just goes over that feeder, Mokopane feeder. So the feeder is quite deep, and then there you also have thick crust. And maybe this is a staging chamber that they were maybe connected, and that the magma flowed in there from the staging chamber. So if I just look at it in do a summary on this, where I show the ternary image and I put the thickness of the lower crust as contours. It's a bit messy, but I don't know how else to do it really, to show them together. So here in this area, we see we have thick crust, we have mafic material, diffuse marrow in thick, dense lower crust, and also we have structures here, big crustal scale structures of the Murchison belt, lineament. With far western lobe, we also have thick crust and diffuse marrow and dense, thick lower crust, and thick lower crust under the Mulliprus complex and mafic material, and so on. And then under the feeders, we also see the crust is actually thicker under the feeder. I mean the lower crust, I think. Yeah. The dense lower crust is also thicker there and here. And once again, here's also a big structure, the sugar bush fault. Not much has been written about it that I've seen, but it coincides sort of with the southeastern limb of the bushveld and where we have this proposed feeder. So all of these things together sort of makes an interesting picture that there is something below something is happening differently under the bushveld complex than under the rest of the crater. So just in summary, for this part, for this section, if we add dense lower crust near the mow, we can model the observed gravity field. And we see that the thickest dense lower crust coincides with the thickest crust, mafic composition and diffuse crust mantle transition. It also coincides with the large structures, and it's also under the proposed or the modeled feeders of the bushveld complex. So there's definitely a connection between this dense material and the bushveld complex at the surface. So the question is then, can it be remnants of the staging chamber at this depth? So what do other people say about the bushveld complex? Why is this important? Currently, there's a debate going on. The one group of people say the bushveld intruded in a big single magma tank, and the other group of people say no, it was a bubbles that intruded, and for at different levels, and also that this is my own weak, feeble addition that you have this transcrustal mush-dominated magma plumbing system from the mantle upwards, and that you have these sort of crustal slurries going up, and in places they pond and make these little staging chambers everywhere, and from there intrude further into the upper crust. This term is from these authors. So what other evidence has been given for staging chambers being under the bushveld complex? I'll just show a few examples. The one is to explain the chromium paradox, and the chromium paradox is that the parental magma that they say,
Yeah, come in.
magma that was parental
Come
to
in. Just
the
open the door, please.
the chromium in the lower critical zone
Yeah, all right.
does not have the right
How's it
composition,
going? Are you
cannot contain the
progressing?
amount.
Super.
Oh,
You can also,
sorry.
please everyone just make sure you are muted.
Okay, so I'm muted now.
Okay. Let's just do, okay.
Thank you. Sorry, I should have done that, I guess. Okay, so yeah, now I lost my track of thought. Okay, so the magma can't explain the amount of chromium is in the lower critical zone, and they proposed, which was Eels and Kosten, that you had a lower, or you had a staging chamber where it mixed with, you had crustal melt mixing with the komatitic magma, and then from there you had slurries that were very much enriched in chromium and placed into the Rustenburg layered suite. Also, how do I get that away now? Maybe if I switch just for a second, switch it off. No. Okay, well, it's in the top section. Okay, this is work that Freddie Rudolphs and Lou did in the northern lobe of the Bushveld complex, where they saw that in the lower main zone, and Lou can correct me if I get this wrong, but they expected for a certain percentage of anorthite in the plateau clays, the magnesium number of the pyroxene. I sound like a geochemist, but I'm not a geochemist. It's lower than expected. And the way they explained it was that you had like you needed a place where this magma was first, I guess, changed a bit. So you had a compartmented staging chamber that was contaminated by different parts of the crust. So, and they used information from the Fairford. We have lower crust and things cropping out. So the one part of the staging chamber was contaminated by lower crustal material and the other part by upper crust. And this will explain the difference in the isotopic disequilibrium, whatever they call it, way above my head. So, and then recently there was thermodynamic modeling. So where they wanted to recreate the composition of the Rustenburg Lake suite in terms of everything, bulk, rock, mineral, isotopic compositions, by doing a thermodynamic model. And the way it worked, and once again, I apologize to the authors in their absence, because this is my sort of interpretation, and I hope I got it right. So, so they say they have this concept of batch crystallization, which is different from fractional crystallization. We have more, I think, more of the crustal melts and material being assimilated into the magma, but then it becomes quite a thick slurry type thing. And you need to move it up through conduits and things to keep it sort of percolating. But that's once again, it's not in my field. So, but that's how I understand it. So in any case, so what they said was that their model can explain the lower crystal zone, that you have this batch crystallization just happening in the upper crust. You didn't need a staging chamber for that. Then the upper critical and main zones, you needed a place in the middle crust where it could, I guess it depends on the composition of the crust in that area, where it could assimilate maybe more of that crustal material. And then that would be in place. So you have a two-stage process where you need to get the right composition for the upper critical and main zones. And then for the upper zone and upper main zone, you have a lower crustal staging chamber to explain the magma composition for those two zones. So why I'm excited about this sort of modeling is that it sort of talks to what we see in the geophysics, that there can be dense material at the crust, in the lower crust, and we modeled dense stuff there. So it looks promising for our model for interpretation. Do we have other analogs to this type of event or way things are being processed in the crust? Well, the one is the Mount St. Helens seismic, the Mount St. Helens area in Washington State. So this is part of a 3D magnetotelluric survey. It actually comes out towards the screen, out of the screen a bit more, where you have these conductors, and you have a conductor in the lower crust, and actually further closer to me, these conductors actually meet up with this thing in the lower crust. And you also have a seismic zone. So along this, which is sort of links the staging chamber with the magma that erupts at Mount St. Helens. That's one. And then this is like real life, like reality TV almost. You have Hawaii, where you had these eruptions in 2020 and 2021. And they actually looked at seismic events there. And they have this thing called the Pahala Cell Complex, which is a staging, which they describe as a staging chamber. And they started to see this increase in seismicity, I think in 2019 or so. And they map all the seismic events here. And you can see the staging chamber and actually some structures from the seismic data. And then in 2020, the eruptions started to take place, those large eruptions that were on TV and everything. So there's definitely evidence, current evidence, that there is a link between deep stuff like staging chambers and things that happen in the shallower in the crust or even at the above the crust. So to conclude, as I said, the gravity modeling shows there's definitely a link between the thick, dense lower crust and these large structures that we see through the bushveld complex. And also staging chambers have been used to explain the sort of complexities, geochemical complexities in the bushveld complex. That makes it easier to explain why we see changes that maybe conventional models don't explain. Thermodynamic modeling supports also the presence of a magma plumbing system in the crust. And we also see this present day examples of exactly this type of a thing. So based on all of this evidence, we feel that the dense lower crustal material are actually remnants of staging chambers under the bushveld complex. We can't see it higher up. I think the data is not good enough resolution. But even if you move this up shallower, you will just have to change some of the parameters, but you can model it. It's not unique. So thank you very much.
Thanks, Julie. Very nice. Are there any examples of benefits like samples of the low parts that we found?
Can't think I've read about in the bushveld complex. No, not that I can think of. Do you know?
Just from the kimberlite.
Yeah.
We've got evidence that there's bushveld material, but I don't think the full suite of crystal analysis has been studied from that particular kimberlite, but there's actually potential there to look for more material.
Just a possibility. The bushveld is littered with groove cells and dikes and complex cells and dikes. There's some of the deeper material lower crust. So the thinking about this could there could be products of staging chambers related to Condo, to Peru, possibly even fences or free.
Yeah.
So it's maybe just like a word of caution.
Yeah.
Some of the sort of that could be undertaken material.
Yeah. I don't show it yet. I didn't show the picture here, but we looked at that. We made the ternary image for the whole SASE data set. And we see the same. It looked differently under the Karoo. Yeah, so yeah.
I'm pretty sure you said that the uppermost mantle, the bushveld complex, is more dense
Yes,
than a normal mantle because it's more iron rich.
yeah,
Is that right?
that's what I said.
Well, that would imply that the storage region where the melts have to be deeper than in that zone because if the bushveld was coming from that part of the upper mantle, it would be depleted, it would be less dense, less iron.
Okay.
So it implies something about the depth of where the melting takes place.
Okay.
Doesn't that make sense to you?
Yeah, yeah.
Okay.
Thank you.
Just means it can come from
From deeper.
the cave. You mean it just doesn't come from the cave?
So it comes from the top, does not come from the lip sheet.
Thank you.
Thank you, and first time I ever gave a talk to you guys.
As long as you scribe your mouth, it's okay. Okay.
I thought early on. We forgive you for having been unmuted. Okay, up next we've got Keith. And you are just finished, well, you're busy with your.
Yes.
Sorry, this is homework I should have done ahead of time. And you will be answering all the geochem questions that Janine couldn't answer on the bushveld. Okay, let's just get started here. Hold on. There, okay. 4 presentations, yeah. Okay, sharing stop, that's fine. Please just remind me to share again. Is that finished? Let's do that. I always struggle. Okay. I'm going to move it onto the desktop. There. Okay, let's just make sure. There, more to run the computer. Okay. No. There, oh yes. Okay, and now she'll see. Do you know how to get this top bit to go away? Oh, this one. Okay. Should we? Okay, we're going to do it the other way. So I'm just going to do share screen because we did share PowerPoint before. Okay. And how do we get this top bar to go away?
It just disappears.
I thought so, but it didn't disappear for. Oh, there. And oh, apologies. I didn't. Okay. And let's get you your pointer. I'm sure you know how to do that. There. Okay. Take it away, please. Thank
Good afternoon, everyone. I'm Peace. Currently in the process of completing my PhD. My work is in the bushveld. I'm analyzing appetite for strontium and neodymium. The topic of my presentation today is the significance of isotopic decoupling in the mafic ultramafic layered sequence of the bushveld complex. Right, so the bushveld complex is located in the northeastern part of South Africa, as you can see from the map that I put on the right. And it's been dated to be 2.06 billion years old. And it's very popular, so I'm not going to talk much about it. It hosts some of the largest PGEs, and we also have chromium and vanadium as well. And it's a hot topic in South Africa because of all the questions that we have in terms of its metallogenesis and how the mineralization formed. As part of my research, what motivated my research was trying to understand the origin of magmas that formed the bushveld complex. The previous work that has been done by other authors who have conducted bulk isotopic analysis. However, because of the previous work, we are able to do this now. We're going to be analyzing, in my research, I'm analyzing apatite as a mineral, not bulk isotope, because bulk rock isotope data can be problematic because of the different crystals and the possibility of different magma batches. So it complicates things. So what do we know from the previous work that has been done? We know that from the bulk rock isotopic data that was conducted, they interpreted them to represent multiple pulses of magma that mixed, and they were ranging in composition and as well as in volume. And they also interpreted them to reflect significant pre-emplacement, crustal and lithospheric mantle contamination of the parent magmas that were responsible for the formation of the bushveld. However, recent work on lutetium and hafnium measured by Sarak Pava and they, throughout the Rustenburg-Leert suite, have shown a limited range in the isotopic values that they obtain. So if you look on the right, there's a diagram with some of the previous work that was done by the various previous authors. From my left, or from the left, we have here where the pointer is, we have hafnium data. This is in zircon that was analyzed by Zerat Pavar. And then if you look at the measurements that he obtained, you can see that there is a homogeneous trend from the lower zones. You get into upper zones, the main zones. And then if you move to the neodymium that was measured by Maya, which is bulk rock isotopic data, you can see there is variations as you move from the lower zones of the Rustenburg-Leert suite, which are also being sort of mimicked by Kruger's data, strontium data, as you can see here. So as part of my research, I'm analyzing strontium in neodymium in apatite to test if this homogeneous signature that we see here in hafnium is there. Is it robust? And as part of it, we can also try to make inferences into the magma sources and the metallogenesis of the Bushveld. We are also we're aiming to constrain the magma sources and the original platinum mineralization. And some of the objectives that I have for this research included trying to separate apatite from these mafic and ultramafic rocks, which is difficult. But I can say that we did manage to find some apatite grains, and also trying to understand the location where we are finding these apatite grains. Are they really accessory phases, or they are not? I'll talk about it more in the next slides, and also show you pictures. And we tried to classify them using major elements in apatite. We used the probe for that to see what type of apatites do we have. Is it fluoroapatites, chloroapatites, and was it another objective was to try and find out if it's possible to actually do in situ isotope analysis on apatite from the Bushveld. And yeah, it was possible. We chose the mineral apatite because it's present in the Bushveld rocks. It gets difficult to separate it from the lower zones, and becomes less and less compared to the upper zones of the Bushveld. But other reasons include it being a major repository of rare earth elements, which we can then analyze as well. So it retains important geochemical information, which can be used to try and understand the petrogenesis of the Rustenburg-Leert suite. Here I'm showing a generalized map showing the locations of my samples. So an important thing to note is that the samples that I'm using are exactly the same samples that were used by Zerat Pavar for his hafnium and zircon, so that we can effectively compare our results. And the methodology involved petrography to try and understand the apatite textures, and then we moved on to mineral separation, where we used the self-frag and we crushed, we milled, we sieved to a size of 125 to 250. We did have, however, have also smaller sizes, less than 125 microns for our apatites. Then moved on to the next stage, which is heavy lipid mineral separation, magnetic separation, all doing all these to end up with a mount where you mount your apatite. After we did that, we then used a Tescan integrated mineral analyzer to try and pick our apatite to see what we would have picked using a binocular microscope was actually apatite. And it also helped us with imaging the apatite to try and see the different internal textures that we can get from it. And then we moved on to EPMA to get the chemistry of our apatite and CPMS to get our strontium data and our neodymium data. This is, I'm not going to spend too much time on this slide, but this is how my samples look like, the one that I have analyzed for apatite. We have a granophyre and granite, the overlying rocks of the Rustenburg-Leard suite, and then in our upper zone we have a diorite, and in our main zone we also used a diorite. Merensky reef, we have a pyroxenite that we used, and lower zone, and so on. So here I'm trying to show the apatite textures as they appear in thin section. So we also put our thin section into the Tescan integrated mineral analyzer to try and see how our minerals are relating to other rock forming minerals. So I'll use here is on your left of the image, in the upper zone diorite, we have a BSE image, which is backscattered electron image, and then on the right we have a cathodoluminescent image. So our apatite, if you look on the right where my pointer is, are these minerals that are appearing bright, right? So you can see from the upper zone, we have apatite that's subhedral and also anhedral, and it appears that most of the grains that we have are occurring close to grain boundaries, and some are actually inclusion inside other minerals. In this case, this is apatite, but it's included in plagioclase. So we have apatite inclusions in cumulus phases, and you can also see as you go down the stratigraphy in the main zone that we have our apatite also included in plagioclase. So to just give a general feel of what we have in the Merensky reef, our apatite then starts to be seen wedged between whole rock forming minerals. In this case, we have our apatite is interstitial in the Merensky reef, but it can also be cumulus, as you can see on the right side of this slide. And then we move on to the upper critical zone. Our apatite, you can see it also, it's occurring wedged between minerals. Here we have a little bit of orthoclase and quartz, and then there's apatite, and this is the apatite on this side. And you can see that it's euhedral here as well. From the mounts, we also took individual images, zooming in into our apatites to try and see the internal textures. Are they zoned or are they unzoned? Right? And generally, what I noticed is that I didn't see any zoning. However, there is, if you look at this image, there's some subtle reflectance that you can see in CL. And I think that maybe because of the different chemical composition of that apatite, but it's not really zoning. So these are where the overlying rocks, and then we move on into the upper zone, and you can see here clearly that it doesn't show any zoning at all. And then in the main zone. So I'll quickly move past this because the images don't show anything that's that different. Here, I have a ternary diagram now showing the chemistry of my apatite. So it's important to know that in the upper zone, most of our apatite most of our apatites are fluoroapatites, and then the main zone as well. However, if we move into the Merensky reef, we found ourselves having two clusters. So we had fluoroapatites, and then we also had chloroapatites. And this can be attributed to, but previous authors have attributed this to an interaction of chemically distinct hydrothermal fluids, or it could be melts in a chemically evolving magma stream. So you end up having two distinct apatites. And we noticed also that our appetite chemistry in the bushveld also falls in a similar range compared to some of the Skagit appetite chemistry that they got. Moving on this diagram, I'm showing the range of epsilon values at 2.06 that we obtained for our appetite. And we obtained an average for about 65 analysis of minus 7.2 plus or minus 4. Please note that these demarcations that I have on this side are not to scale, but just to help with visualizing this plot. As you move from the upper critical zone, we didn't have any appetite. We didn't find any appetites in the lower zone. It was really difficult. But in the upper critical zone where we had our appetite, we could see that the values were ranging from -8 to -10 for most of our samples. From -8 to about -9. And then in the Merensky, it's important to know that we have like more negative values, which are non-radiogenic, and they correlate with some of the hafnium values that we found in zircon. On this diagram, I have a table on this side where I compared my average appetite neodymium values to the average bulk neodymium values of appetite. And you can see that we have different compositions in the Rustenberg-Laird sheet stratigraphy. And this can represent isotopic decoupling. So if you come to this diagram here on our left, this is Myers data. So let's focus on this and what I have here. So you can see in the main zone, Maya had values ranging from maybe -6 to around -7. And I had values ranging from -6, somewhere here, which just to emphasize the isotopic decoupling that we see. This is preliminary work. So I tried to plot some of the strontium data that I have on top of some of the work that was done by Julie and some of the isotopic data that was measured by the bulk isotopic data that was measured by Kruger. But what's important to notice is that our values, our strontium values didn't overlap with the bulk rock. They are pointing or leading towards decoupling. So the same on this diagram as well. The red is my main zone samples, and here the main zone samples have a down-facing triangle, but we can see that the samples are not overlapping with these ones, suggestive of isotopic decoupling as well. The key findings from this research, we found out that appetite is an accessory phase in the Rustenberg-Laird suite. We've seen it also occurring as interstitial in the pictures that I've previously shown in this presentation. They are relatively homogeneous. However, some grain show like those compositional variation that I was talking about. Appetite is more abundant in the upper zone as compared to the Merensky, and it is pockets or fractionated material, and sometimes it's hosted within minerals. Our EPMA data showed us that the grains that we have in the upper zone are mostly floral appetites. That we have appetites that are more chlorine enriched. In terms of isotopes, there is a difference between the Merensky chloroappetites and the rest of the floral appetites. And neodymium values that we had were more negative compared to the other parts. In conclusion, we concluded that our appetite values show very minor variations in the different zones of the Rustenburg-Gliad suit, which is similar to what was found by Zulakpava and Zeh for the hafnium in zircon in the Rustenburg-Gliad suit. So this supports the evidence that the mineral isotopes are homogeneous compared to the bulk rock isotopes. Our preliminary strontium data in apatite is also consistent with some of the neodymium data, further showing mineral and bulk rock isotopic decoupling, as shown with our preliminary strontium data that I plotted against other people's isotopes. We therefore speculate the origin of this isotopic decoupling with the following hypothesis that I'm about to mention, that maybe we had melt percolation in the crustal marsh that led to isotopic homogenization of the trapped melt, or there was emplacement of isotopically distinct cargoes of silicate crystals in the isotopically homogeneous carrier liquids during the emplacement of magmas into the Rustenburg-Gliad suite. Also, just to acknowledge the use of these instruments, it's very useful, especially for the Bushford and the ultramorphic rocks. It's very difficult to find the apatite. So sometimes if you rely with instruments like the Tescan integrated mineral analyzer, you might confirm for yourself if there's actually apatite or if there's none at all, using thin sections as well. Thank you.
Yes. So you're using apatite to tell you something about the major melts and magnets of the bushveld.
Yeah.
But how do you know that the apatite might not come from the crust? Because you have crustal contamination.
Yeah.
Noticed and measured and modeled by everybody. So how do you know that your apatite doesn't come from that contaminating component?
According to what I've been reading, this may not be the correct answer. What I have not done with my apatite so far is to do in situ trace elements in those. But I've seen other authors that have done trace elements in apatite, and they've used the rare earth element diagrams that they find from there as discriminatory diagrams to sort of point out the melt that they have or where it comes from. So I've not done that, but I think maybe if I do that, it might be helpful.
Thank you. We can't hear you. Oh, okay. So you want to
Yeah, please, I just want to check with you in terms of quantifying the patterns that you're seeing in your stratigraphy, because I picked up you mentioned that you see some homogenization pattern in the neodymium data. Have you tried to quantify it using looking at the stationarity, looking at your mean, your variance to better quantify for the patterns that you see in your data set?
Yeah, so what I've done so far, I've used the variance to see how my different measurements vary from each other, and also how the amount of error that we have in our measurements to try and quantify that homogeneity trend.
Any other question? Thank you very much. Thanks.
Thank you.
Which one is your, can you put it on?
Again, next is Camilo, who's busy doing her MSc, and this is an example of some of the weird and wonderful ideas that Sue comes up with. So Sue had the idea for this project, and Camilo was brave enough to give it a try. Just a disclaimer, we've been having some data problems that we're trying to sort out, so we haven't actually got the high resolution data that she's going to need, but we'll expand the concept, show you some interferograms that she's got, and yeah, just give us an idea of the way forward as well. Thank you.
Hi everyone. Hi. How are you? Okay, so I'm going to be presenting my research, which is titled Using InSAR to Detect Soil Expansion. And the whole point of this is to try and use InSAR to explore for kimberlites. My supervisor is Steph and my co-supervisor is Sue. So as we all know, kimberlites are the most important sources of diamonds in the world. But because kimberlites come from so deep in the Earth's surface, when they get to the surface or near the Earth's surface, they become very unstable and weak. And so they become hard to find. Sometimes they're just inaccessible and become buried, so they become hard to find that way. So this gives rise to innovative exploration methods like InSAR to narrow down the probable occurrences of these kimberlites. So in 2003, Mark Hamilton and Susan Webb, in their paper called Delineating Kimberlites, they noticed a seasonal surface elevation variation over a known kimberlite pipe that they were studying. And they attributed the surface elevation variation to an increase in the kimberlite clay moisture content during the rainy season and a decrease during the dry season. So InSAR is a technique that can detect millimeter scale deformation using electromagnetic waves and an orbiting satellite. So the kimberlite of interest here is located in the Northern Cape, about 56 kilometers west-northwest of Kimberley, the town of Kimberley. And in the small image here on the side, you can actually see the expression of the kimberlite in the Google Earth image. I couldn't find a very good geological image to georeference, but we can see here that Mark's kimberlite is found in the Fenterstorp supergroup. In the local geology, most of the area is covered by the Fenterstorp, the volcano sedimentary sediments of the volcano sedimentary rocks of the Fenterstorp supergroup, as well as the Draco and epicubes and intrusive dolerite dikes of the Karoo supergroup. Here we also see that the kimberlite is mostly covered by Aeolian quaternary sand sediments. Previous geological studies have been done in the area, including magnetic, electromagnetic, and elevation studies. But most of them also require ground techniques to be applied in order to accurately delineate these kimberlites. These are the results from the elevation studies, and you can actually see the shape of the kimberlite and the elevation variation. These are the gravity results from Sue's paper. These are the magnetic results. And these are the electromagnetic results. And this is a combination of all of these delineations. You can see in black the elevation, the gravity, and they all come together and kind of show the shape of the kimberlite. So in conclusion, in their paper, They highlighted that the high topography over the kimberlite can be a very useful tool in delineating the kimberlite, and they attributed this to that yellow area holding most of the water that is collected during precipitation. So INSO can be used to detect this topographic anomaly. So INSO basically uses radiomagnetic waves that are transmitted onto the Earth's surface and reflected back to the satellites to calculate the distance between the satellites and a point on the Earth's surface. And this is done at varying times as the satellite orbits the Earth. So calculating the difference between this phase data that is collected by the satellite can be used to calculate the deformation that took place at that point that the waves were transmitted onto. To kind of guide my research, I reviewed this paper by Theron et al., in which they used high-resolution TerraSAR X data with a resolution of 2.7 meters to detect a sinkhole in a carbonate underlain area in Centurion. And they didn't use multi-looking, so that was a very important factor for me, because multi-looking is a process that uses the surrounding pixels of a pixel to create an average value and therefore increase the coherence of the data, but it reduces the resolution of the data. Theron et al. Were able to confirm a single deformation event out of 3, and you can see it here in these images. The deformation, the sinkhole was 60 meters across, and over time it increased to 7 meters deep. So 70 meters across and about 7 centimeters deep. And this is a line of sight displacement map that shows a maximum diameter of 80 meters for the cell and a subsidence of 5 centimeters over the 55 days that the data was collected. In 2018, then it all reviewed several factors, several things to be considered when using INSO, and they highlighted an incident where INSO was used to map the deformation caused by aquifer overexploitation. So using this line of thought, I assume it should be able to map the loss of water at a kimberlite. Theron et al. Also highlighted the fact that changes in atmospheric and surface moisture can introduce error to the interferometric results of the data. And one important thing to note was that the colors of the interferogram are not an indication of the magnitude, you can't tell the magnitude of deformation just by looking at the colors. You have to look at the scale first, so you can get oranges and blues, and it can still be the same deformation, depending on the scale. And there are a number of limitations to using IMSA, such as the resolution, the subsidence rates, the moisture levels in the soil and the atmosphere, as well as the soil cover where the study is being conducted, as well as the temporal baseline, which is the time taken between data acquisitions. So the smaller the temporal baseline, the more accurate the results are. The bigger it is, the more error there is in the data. But this can all be combated by picking the right source system, by picking the right processing parameters, and paying close attention to the atmospheric and surface characteristics at the time that the data was acquired. The aim of my research is to explore INSAR as a way to explore for kimberlites, and the objectives are to review the occurrences of kimberlite pipes, as well as the applications of INSAR techniques in real life situations, as well as to create interferograms of known kimberlites, which is the one Sue and Mark studied in 2000. Failed setting. So for research, I downloaded data from the European Space Agency, which is free. And I then imported this data into the Snap software, processed it, and then exported into Google Pro for visualization. Ooh, the methodology was fixed. So the first part in this block is called the co-registration process. And in the co-registration process, so at the bottom here, these are all the files that are produced and that are input for install process. So the first two files are the red files that are input into the co-registration tab. And then in the top source split process, the correct area in the data is collected. So there's 3 different SWATs, and you have to select the correct one that has the target point. So in the top source split, the correct area is chosen. In the apply orbit file, the orbital position of the satellite is considered in order to be able to align the pictures accurately. And then the back geocoding is to put the pictures together. And then combined data file is produced. And then from this, I create the interferogram, and that's the one with the orb stack suffix, and then the data is debursted. So okay, this is very complex. So I'm just going to go through it very quickly. And then the topographic phase removal is connected to. Okay, let me just find my words. The topographic phase is removed in order to just leave that differential component. So the deformation component only. And then multi-look is the one that creates an average of the pixels to increase the coherence. And then the filtering to remove atmospheric contamination. And then terrain correction is where the radar coordinates are then transformed to geographical coordinates of longitude and latitude. So last year, I didn't know the importance of temporal decorrelation. So I collected a data set that had a temporal baseline of 6 months. So these results are probably bogus. But I was expecting subsidence and instead saw uplift. So yeah, that's confirmation that they were incorrect. And then these are my most recent results that have a temporal baseline of 12 days, which is the temporal baseline of the Sentinel-1 satellite. So this is the best we can get. And here on the left, we have a non-multi-looked interferogram, and on the right, we have a multi-looked interferogram. On the non-multi-looked one, we see that there's a decrease here of the signal, which means that there is a decrease in the distance between the satellite and the surface of the ground. So this means that there was uplift. But this is too big an uplift for 12 days. So I think it is very important to apply multi-looking. I didn't think it was, but now that I'm looking at the results, I think it's very important to do multi-looking. And on the multi-looked one, we see there is no deformation. It's mostly green, which is close to 0. So there is no deformation there, which makes sense. Moving forward, I've decided not to use multi-looking to get more accurate results. So here we have a picture that is multi-looked on the left and non-multi-looked on the right. So there's a very big difference that multi-looking does contribute to the picture. So I will be using multi-looking going forward. And I'm considering downloading TerraStar X data in order to get high resolution data of my kimberlite. And I will be collecting all the data basically in 2022 with the temporal baseline of 12 days each in order to get more accurate results instead of using like longer temporal baselines of 6 months like I did before initially. And that's it. Thank you.
Very much for the software and learned it. Any questions?
It's more of a statement. We've been living city well, and if you also saw the astronomical millimeter thing, And then you did a lot of processing and noticed that you gave you big shifts and stuff like that. We ultimately realized some more probably more into the atmosphere than anything else. So there are two techniques that they use to overcome this. The one is called SBAT, which stands for full baseline barometry. The other one is called persistent static barometry. Both of them are kind of like stacking techniques. The persistent static one is used in buildings, so that's not really useful. The SBAT one is not. And they require like about 60, 32 seeds or whatever, so that's like a year's worth of seeds. But they actually give a little lot of the other columns, and if you're looking for small shifts, I think that's what people we tend to use when they're doing it. So I'm just saying that if you don't get what you're hoping to get, what you're doing right now with INSAR, which is very spectacular when you have a big earthquake, a big shift, but frustratingly not, then there is hope. Now, I don't think SNAP does express directly, but I think it has an export to a package that does really express. One of it's being used and stuff like that. So it's just worth looking into considering. Once you've got everything together, it's not such a big deal. I think it's like stacking the averages, the errors, and try to need something to see. Then you can actually, in any at any rate, you can actually see the training shift over time. That's good. We are using ENV, but we also played around a lot with Snap, and so the person that actually does this council, Gary, and he's actually went out with one of the colonels of the Air Force, who seemed that they're doing processing there as well, and he's into this kind of thing with the economy. So I think that there is actually a lot of, you can pretty much do it all on open source. I don't think you need something expensive like the ENV necessarily. Just any is like a nice complete package that everything works. Okay. But I don't think there's nothing wrong with using Snap, and I know that there's a video options coming up with another article package. You can look at that. If you struggle away around always finding normally what it always finds it find itself.
Results images on this map. Big, like where is the kimberlites?
The kimberlite is very tiny, and no, it's a very tiny. It's about you see the scale here is 10 kilometers. The kimberlite is like 150 meters. So
that's why the new data was looked at to small level. So yeah, that's more of a reason.
Understand the first question in the description, like your descriptive image of the kimberlite of black, will check on the top. The change that you're looking for, is it in the actual kimberlite, or you're looking at the flag or the check that is there, and you're looking for an increase in volume of that rate?
an increase in volume.
You're looking at the change in the distance between satellites and soil, right?
Yes.
So you're expecting the difference to decrease?
It depends on the date. So from the rainy season to the dry season, expected to decrease. And then from the dry season to the peak of the rainy season, expected to decrease. And shortly afterwards.
And it's the way that soil.
It's the
1.6 meter. But it should be.
I think the most important part is just
On the left side, the cumulus kind of the whites. If you take the regional out, remove the average. It's about 1 meter. What is And just as a side question, would this method kind of work if you looked at it over like no, that was last week. It had a huge raise. I mean, like you take the 12 days that are appropriate and 12 days before you think it would work on a shorter time scale in real life.
I think that's still also a question for me.
But you also showed the sinkhole day. This showed variation.
Oh, yes, they could show, they could, well, they had a small temporal baseline and had a small temporal baseline and the subsidence that they can detect is like up to 3 centimeters and the smallest is like 1 centimeter. So I think you can. Still a question.
I think this was Tara's. Control is.
Have you considered setting up a weather station with a GPS, only GPS?
I have not before. I just,
And security.
Because looking at the rainfall data would be.
One year ago, so.
Thank you, okay, well, that sparked a lot of discussion. We have two now that is upstairs in, because at the same time.
Yeah, the tea will be at 3 o'clock, so we've got to finish a little bit early. So we'll have tea and then try to. Back and. Okay. Yeah.
If you are talking after that, please find those reports.
During the tea break. So for everyone online, we will be back at 3:15. Thank you for joining us. And then we can get started. So Mustafa, do you want to come up? He's a PhD student. He's finishing up for Musa. And let's just check. Did I put it over here? Okay, so we're moving over from the bushveld to the gold fields. And I am, wait for it. Playing. Okay. Well, let me just check. Am I? Okay. Well. Who's replaying? Should I stop and start maybe? Yeah. End meeting. Stop now. You know what I think it might be? There is. I think it's YouTube. Fletcher.
No.
But I can switch it off. I don't have to have YouTube running to live stream it. I could, that is a good point. I know, I'm just trying to get to the top of my screen so I can right click, there we are. So I'm going to right click, mute site. Just double check. I'm going to switch that off just so we don't have multiples. Okay, so it is running. We know it's running. It's just a bit delayed. We are here. We're sharing the screen. We are unmuted. Let's maximize you. And let's go to laser pointer. Okay, so Mustafa, take us away. Thanks, everyone.
Good afternoon, everyone. My name is Mustafa Ndamero. I'll be taking you through the reappraisal of legacy reflections and data for exploration, for gold exploration. These case studies from with veteran goldfields. Okay, this is my outline for my presentation. Yeah, for introduction, I'll start by defining the legacy data. Legacy data is data that was acquired a long time ago. That was maybe pegged somewhere else. So what we do, we try to revisit that legacy data to reprocess it and interpret it. So for this case, I'll be presenting two case studies. Case study one is the one that is near Clough-Driefontein Complex East gold mine. And the second one is a study area that is closer to South Deep gold mine. For case study one, I'll be targeting a body of Black Reef, Black Reef. And the case study two, I'll be targeting the VCR, ventral contact reef. Yeah, so the mining industry has long relied on traditional geological mapping and drilling for mine planning. So, however, there is a growing recognition in exploration, especially for deep targeting ore body. So, for that, that's why we came for our reflection, for seismic method to do reflection seismics. So the main aim of this, the main aim of these studies of these study areas is to reprocess legacy seismic data and image the mineralization and also image the geological structures that may cross-cut our mineralization. So for case study one, I'll go through, I'll be reprocessing the data to image our Black Reef mineralization. And also I'll do the numerical modeling for seismic to test the seismic reflectivity of some of the units on the study area. So for geological settings of my study area, we have from our picture A there, we have what do you call this? So see the dotted rectangle there. That's why my study area for case study 1. Here I was processing two legacy seismic data, OK212 and 213. And this line, if when you see on the geological map and B here, by the color of brown here, this one's representing the Malmali subgroups. So as we know, for our seismic data, when we acquire our data with our vibro sizes, so here we have outcrops of dolomites. So these dolomites are the one that attenuate the reflection below the dolomites. So it's hard to get reflections if we have these dolomites on our seismic lines. So for this study area, if we check our this site for geology, the stratigraphy, we observed that in this seismic line, we didn't have you see this red outline. So on this red outline on our study area, we don't have these units formations on our seismic data. So only have this side from the Transvaal supergroup. Then from Transvaal supergroup, it went straight to West Rand supergroup. So this, I'll go through these acquisition parameters for our line. This line was acquired in 1988. It was 2D. Yeah, these 2D lines. So what I did, I was processing these two lines simultaneously. Yeah. So the first, the OK212, it has a proper length of 16.9 kilometers. The other one is 15.7 kilometers. So both of them, they have a sampling rate of 4 milliseconds. Yeah, so they also they both use the vibro size as a source. The source spacing, it was 100 meters apart. So for numerical modeling, so what we do, we kept our raw data parameters so that we can compare our modeling results with the raw data to see and test the source of the reflectivity of our reflections. So I kept for this, actually for numerical, I only did the modeling for OK213. That looks, I think, if I show you here, is this one over here. That's only small piece of that crosses the Malmali dolomites, because there was no need for me to do this one because of some of the reflection. We know that we can't be able to see them underneath our dolomites. So I only processed, I only created a modeling for this line over here. So this the model that I created. We use the velocities and densities of the published authors in the study area. So here, I created two artificial balls to just check the reflectivity of the area. So I created one that is here, and the one that also cross-cutting possible leg reflection. So these are some of the published values that I got from the previous studies. So what I did, I went through and did a 1D synthetic modeling for seismograms. We had a 55 hertz for dominant frequency on our seismic data. So I kept it also for the modeling. Sample rate I did, it was the same, 4 milliseconds but for wavelet here, we use the Richter scale. So after I created the model, this is the results for 1D synthetic modeling. So from here, we can see that we can be able to see the source of our reflectivity here, which is between the Hospital Hill subgroup with the basement. That's where we were able to see high amplitude from our synthetic seismogram here over this side. So also for this side for the yellow one, I also did the same, which we were able to see some of the reflection that's coming up here. You see, that's where it's coming from between Malmali subgroup and the hospital group. So this is the one that is within the Black Reef mineralization. So what we did, we used this inverted rectangle. That's where we're gonna use get our example of a short gather from our synthetic, and also I'm gonna compare it with the real data that we got from the legacy. So what I did, this is the results that I got. Since I kept the parameters the same, so I chose the same shots, which was a shot number 129. This was showing with the first breaks that are represented by the red arrows, and also these green arrows that is representing a possible mineral, a black reef mineralization. And this blue over here, it's representing the contact between the basement and the west rand group. And then this respective amplitude spectrum for the synthetic shot and the amplitude spectra and raw shot gather. So for processing, we went and we read in the data, then we had to do the pre-processing, this geometry and CDB. So one thing about the processing and legacy data is that legacy data has its own advantages and disadvantages. So one of the advantages for legacy seismic data is that most of the data is not contaminated by noise or mining noise, and also that's compared to the new data that you can acquire now, it's much cheaper to reprocess legacy data. So one of the disadvantages of processing of legacy data is that most of the data are stored in the old tapes. So most time we might find that the data or the headers they don't have coordinates or elevations. So what we do, we check that first and see if we can be able to recover some of the information from the headers file. But most of these lines, when they come, they didn't have a coordinates, they didn't have an elevation. So what we did, we went to SRMT data to get our elevations there. That's what I did. So most of the time, yeah, this is the step that takes time when we are dealing with the legacy data. So the next step after doing those geometry setup and everything, we went and processed the data. And then this is the crucial step, this is the velocity analysis. So here, that's where we check we deal with our velocities for velocity modeling. Yeah, so here we know that from previous or all times when they process the data, what they did is that they say that the velocities increase. We know that the velocity increase when we go with depth, but now with our and new softwares, we know that that's not the case, because sometimes you might find a layer or unit that is below below that. So what I did here, we tested a few we tested the pre-stack time migration and pre-stack depth migration. It also tested using the post-stack time migration. So I'll be presenting the results for those. Yeah, these are just some example of short gathers, raw and process, just to see if we are getting a good reflections after processing. Yeah, also what I can say is that most of this data, most of the shots, actually, most of not all of them, they applied notch filter. That's where you can see the DPA on the amplitude spectrum. That's where they applied notch filter. So for applying notch filter is when we have a big spike that is caused by maybe power lines around there in the study area. So also we can see by the white arrows here, this might be ground rolls or the airwaves. What I did to attenuate them, I applied FK filter to attenuate them from our processed short gather. So for the next results, I did refraction tomography velocity model for our line. So I did for these two lines. For this reflection tomography is showing us 3 distinct layers, the topsoil, weather soil, and the bedrock. So yes. So we move on. Yeah, this is the result for the other two, the other line, the 2 and 3. And this is the right path for profile. So for the results, this is a post-tech time migration. So this one from 212, if you can see on the top, this the top rectangle, these ones are representing the surface geology on the study area. So if you can see here on the top part of our seismic section, is showing that there's no much showing. So this thing is what it's doing is it's attenuating all the reflections below these dolomites from the Malmale subgroup. The only thing that we can see that's popping up is where I put this red outline here. That's where we see our reflection coming up. Yeah, this is just a enlargement of this red rectangle over there. So for me, to put these reflections, this R1, this due to the contact between this layer here and this layer, which is a export formation and the time ball hill formation. And also when you go towards the south, that's where we get our mineralization, a black reef. That's where I represented using these arrows over this side. And R2, that's this side of this section towards the south. Yeah, so also this is the post-tech time migration for OK213. Yeah, this one is really showing some of the reflection coming up because we only have a short of the short portion of the Dolomites. So this is showing the enlargement of this post-tech time migration. Yeah, this is the results where we were able to see our black reef just below the R3 that's over there. And these are just deep reflection that is happening maybe on the western group. Yeah, so in the big case study, we'll be comparing a pre-stack time migration and pre-stack depth migration. So on this side is for OK212, the one with the most of the line that is that has dolomites along the line. So from here we did interpret. We found before I go there for interpretation. So we are comparing 2 different things here. This one is in depth, and this one is in time depth. So in time. Yes. So what I did first, I had to convert our pre-stack time migration to depth. So what I did here, I used the constant velocity of 6,000 meters per second because of the rocks that we found in the West Basin. So this side, I also did the same thing for OK213, where I was comparing the pre-stack depth migration with the pre-stack depth migration. Yeah, this one is for OK213. This yeah, we're able to map the CDP close to CDP 480. Yeah, that's where we'll be able we're able to image our black reef formation. And this side we have a R4, which is coming from south to north from the CDP 230 going towards the north. Most of this layer or units are dipping towards the north for OK213. So for my interpretation, for here, I didn't have bold data to constrain my interpretation. So what I did, I used the surface geology. That's why I put this square rectangle for the surface geology. So this interpretation is based on the surface geology. Yeah, so this was my interpretation where we get our black reef. This dotted, I'm not really sure if the black reef is continuing towards the north for this profile. So for profile 213, I found out that this was a bit difficult for me since I only did geology 1. So the geology for me, it was dealing with me. So, but towards the end, I found out that for this profile, it was deep in this hospital Yale subgroup. It was deep in both to the north and the south. So because we can't favor this government subgroup that it can be below the Western group, because that it means that here we had a what do you call this? Yeah, the dome, like, yeah. So we move on to conclusion for this. So we were able to improve the quality of this the data after initial reprocessing. So we also found out that the pre-stack depth migration is good for mapping the deeper reflections, and the post-stack type migration also good on mapping the shallow reflections. So there's the data for, especially for 213. Okay, 213, it was showing a higher resolution and better continuity of reflections. And as we saw this from the geological map, where most of these 2D lines were characterized by most of the dolomite outcrops from the Malmale subgroup. Yeah, let's move on to the next case study. So for the next case study, we're still doing the same thing. We're reprocessing the legacy data. But here, we chose this study area of sub-deep gold mine because here that's where, because the last one I couldn't have, we didn't have the VCR. We only had a black reef then. So here we had a VCR, and for this time we only chose to use one catch-off pre-stack migration. We didn't use the depth and the post-stack. So the geology is still the same and in the same area. So for this line, I was able to get hold of the boreholes data. This the line. This is my 2D line, and this dot, this maroon, yeah, this 1, 2, 3, 4. Yeah, these are where my boreholes locations are, and this star over here, that's where the sub-deep mine gold is. So yeah, this generalized stratigraphy of the study area, where we have a black reef at the base of the Transvaal supergroup, and we also have a Ventersdorp contact reef at the base of the Ventersdorp supergroup. This is a contact between the Ventersdorp supergroup and the Central Rand group. Yeah, this acquisition parameters, where this line was acquired in 1983. For gold exploration, I think it was acquired by Anglo Gold. The line is 25.3 kilometers. Yeah, here, one thing to note, when we check in from the previous case study, the one thing that they did here, they use a end-on field spread. So what they did, the last one, it was a split spread. So what most of the short gathers, they will be looking like this on the split spreads. For this one, for end-on, so what happens is that most of the data, they will be acquired, they will be looking like this, going from this the start, they will be going towards this side only when you are moving along the profile. So the shift frequency they use, it was 10 to 10 hertz, and they use 4 vibrosas. They were in line, they were shooting at the same time. Yeah, so for this line, they only had an active of geophones or receivers of 96. at a time. So we will move on to processing flow. Yeah, we still use the same thing, but here we only focusing on pre-stack time migration only. Then after that, we converted the pre-stack time migration just to compare with our bowls, because the bowls that I got, it was only in depth only, so I couldn't get the velocity seismic thing and the densities to do my modeling. So for this line, we were able to, it was still, I had the coordinates for, I was able to extract coordinates for this line. The only thing that I didn't have, it was the elevation. So to get the elevation, I did the same thing. I went to SRMTM site and get a TIFF file where I had to extract elevation depending on the coordinates that I have for my legacy seismic data. Yeah, so these are examples for my short gather. These are only comparing the raw and the raw and the processed. So from here, the red arrows, they are only showing the first breaks. And the black ones, black arrows are only showing ground rolls or air waves energy. That's you know, on our raw short gather. Also here, where they did apply notch filter on the field. That's why we have this dip here at around 50 hertz. And reflections, I represented them using the blue arrows. Yeah, so for this from this side, what I did, I created this these plots, just to check the quality check of the face and inverted thermography models. So on these plotted functions, these are the plot functions or functions of offset, where the n is the number of points within the range of the travel time plots and travel time residuals. So these are my results, also showing 3 distinct layers. Or yeah, so for my layer, the top layer, it was just showing velocities of 1,000 to 2,500 meters per second, and also the layer 2, I was able to get a velocity of 2,500 up to 5,000, just 5,000 meters per second. And there's the red ones here. I was just this is just greater than 5,000 meters per second. So this plot here is just showing us that we can't interpret some of the stuff that on the pink here because of our ray path, because it means that our rays didn't travel through this space here. If you can see, it only ended somewhere here somewhere here. That's why this pink, I can't really interpret what it is for this section. So for the results, so the results were convincing. So what happened for this line? We were able to also recover legacy stacks. This was reprocessed long time ago. So what are the legacy stack, and this is my stack that I reprocessed. Yeah, so we can see from here highlighting where we have a nice continuity of reflections and visible reflections. So the next part, I'm just gonna show the zoom part from the previous image. So here also, just showing from our legacy seismic data. From a legacy data stack is showing a poor imaging compared to our reprocessed stack. Also, this side, it's also showing. So we were able to, from this stack, we can also see the displacement, which could be interpreted as a fault that's going through our seismic line. So we move on to our results. This is the results for pre-sector migration. We were able to identify few reflections, and also we interpreted this bottom reflection, or reflection as our VCR, because we know from the previous studies that our VCR is seated at 2.4 kilometers up to 3.9 kilometers. So, but here, since it's a pre-sector migration, so it's in time, what I did, we had to convert this to depth so that we can see if that's where it sits. Then this is I'm gonna show the results for the depth on the next page. Yeah, this I'm just showing the borehole logs for that I was able to acquire. So for my line, only these three boreholes, borehole BB1, 1, and DP7 are the only boreholes that are close to my profile. Yeah, this one is a little bit far, so I use this three to consider my interpretation. So we can see from these boreholes, or the borehole one, this one, it didn't intercept the VCR, so it ended up to 3.5 kilometers. Yeah, which means, as we can see from here, our profiles are dipping towards the southwest, from northeast to southwest. Also confirmed by our boreholes, which are also dipping towards that side from this boreholes log results. So the only thing that we were able to see, our conglomerates are on this borehole DP7 and the borehole BB1. That's where we see our conglomerates for our VCR. So for the interpretation, that's where I added the boreholes on my seismic section. These are converted to depth. So they're in scale. This boreholes, like, they are in scale with my seismic section. So we can see that these two, DP7 and BB1, are the ones that intercepted our VCR. So on the seismic section, also showing some of the faults that are cross-cutting some of the units, and some of the faults they went through and cross-cut some of the mineralization in the seismic section. So from this side, that's where on the seismic surface geology, that's where we see that we have a cyanide a dike on this section. That's where we have some of the displacement for if you can see the fault 6 over there. So I did the same thing here for when I converted my section. I used 6,000 meters per second, a constant velocity of 6,000. Yeah. So for conclusion, the use of where we're using the new algorithm to improve the quality of our legacy seismic data, and also the data our seismic section, we're showing a higher resolution and better continuity as compared to our legacy stats. Yeah, we were also able to improve imaging our VCR body, and we did manage to map to image the faults that are cross-cutting some of the mineralization. And so this new information that we are getting from our seismic data, they can be used to evaluate the surrounding of the mines, especially sub-deep. This also can be used to assess some of the deep targeted ore body, as I think sub-deep mine is trying to mine towards the towards southwest. Yeah, southwest. That's where we see from our section that our VCR mineralization is going deeper, going that side. Yeah, these are my acknowledgements. Thank you.
Thank you, Richard.
Any questions? You all in favor now on shop gathers and.
Thanks, that was a good question. I've seen many presentations on reprocessing seismic data. Using just the seismics as well as integrating other sources of subsurface information. Has there been any developments in terms of developing numeric indicators of the improvement in the quality of seismic? I see some of your observations on the ship, for example, an increase or an improvement in reliability.
Yes.
Is there anything that we use as a metric, that's numeric, calculated from that seismogram that would give you a measure of goodness?
I think what we can calculate is the acoustic impedance. You can check because on some of my seismograms there, we had some of the units have the same velocities, but they were different densities. So, but we can still pick up the reflectivity there because of that, because of the much difference in density. Yeah.
I think I've been looking at a lot of oil and gas things last week, but like they like to do these amplitude and bars and drop. We did that with still continue to do. From the amplitude, I wonder.
The way you're asking, it looks like a quality 3 of the ground with the quality 6.
Yeah, I mean, most of the assertions are very objective. I mean, apart from cross-validation to drill holes, just wondering if there's been any developments as a result of looking at well.
That can be very first. First, I think it was a one I asked online, why did you not use the migration velocity model for the time to data conversion?
I didn't use that because of more from the previous case study. That's I used the constant conversion, constant velocity. So I only use that because it worked on my data there. So since it's still on the same study area or the best basin, so I just use that on. But I can, since I have my velocity model in there, I can also use that. Yeah, I didn't use it.
We lost it, we heard about how the new processing, like a new acquisition of seismic data becomes so much cheaper. So in comparison to the new technique without using it in the field to apply it, which is so much cheaper than the cost of acquiring the legacy data. Is it still cheaper to repurpose legacy data compared to doing new data and perhaps data?
Yes, it is. Yeah, it's better to, I still cost less to reprocess legacy data than acquiring your data. Yeah.
The new data and have data resolution like does it apply many
So for that, I think for new acquisition, especially if we're acquiring close to the mines, the problem with that we encounter there is noise, maybe infrastructure noise or some of the blasting in the mine. So for legacy data, most of the data they don't have those noise because they were acquired before the mine. It was there. Yeah.
The social commentary that you pay our students about. They would pay our students more if we can cheaper to acquire and do. Thank you very much.
Thank you.
Cool. Next up is Sikarela.
Presentation.
Which one? Top one.
Yep.
This one. Yes. Okay. Don't even know if it's underneath either. Top one.
You remember the invite?
No, it's just, and we're trying to use this one because they records up. Sorry. And it should still be, and it should still, I'm gonna do it, I'm just gonna stop just to make double, triple sure that we share the screen. Okay, there one. Animated one, so let's just go down here and turn on your data. So try and use the thing. Okay, so next up is Sikalena, another one of our PhD students who's very close to submitting, correct? Well, we don't want to ask. Who's we sure it'll be Santa. Presenting on groundwater vulnerability using integrated geophysics. The reason why I have to look is Sikalena has quite a range of different things. So you're a man of many skills. Okay.
Hi everyone. So as Steph said, my name is Sikelela, and I'll be presenting on assessing the vulnerability of groundwater in the bushveld context. Okay, so if we look at the temperature changes over the African continent.
It's try to turn on the microphone, but you're going to speak loud.
Okay.
Does anyone know, Zube? You don't have experience with.
Hello.
I'm sure they can, but for us, can it not come through the speakers? Talk loud. Okay.
Yes, I'll try to. Okay, so yes, this is the presentation that I'm giving. So I have to say that unfortunately I'm working you guys a bit because there's another case study which has been published and stuff that I worked on, which I'm not presenting on in this case. But then I think this is an interesting one that more people can comment on. So looking at the temperature anomaly change over the African continent since 1910 to 2020, we see that drastic temperatures have occurred, which are said to cause huge social and economic problems, as warmer temperatures promote droughts, which enhance things such as evaporation, that reduce the availability of water, mainly surface water, which also affects groundwater, because the less surface water there is, the more you pump groundwater. And then they dry soils and reduce the suitability of vegetation to grow. So looking at natural disasters in sub-Saharan Africa, that is starting from 1970 up until 2020, we do see that there has been an increase in disasters such as droughts, floods, epidemics, and storms. And also this increase in these disasters is reflected in the number of people affected since 1970 up until 2020. So one thing to know is that in South Africa, natural disasters or such natural disasters have led to huge social and economic losses. For example, what happened in KZN, what has been happening with farmers in the past, I would say 10 years or so, which is related to drought of water and their ability to produce food. So as the availability of water decreases, the demand for water increases, thus the management and protection of groundwater resources become very important, especially in countries like South Africa, whereby groundwater hasn't been exploited that much. In the past few years, for example, we all know that in the country they have been proposing and looking into extracting more groundwater so as to try and compensate for the droughts that have been occurring. So in this case, so when we wrote this paper, I'd say that the main aim actually was to show or highlight some of the gaps that can be filled using geophysics, or let me say some of the near surface problems that can be solved using geophysics. One of the things that we do know is that as much as we're looking to exploit more groundwater, we don't have a lot of information on groundwater in South Africa. So in order for us to be able to utilize it properly, you have to study it more. And yeah, so in this case, we were just trying to show the usefulness. So the secondary aims are, which in most cases would be like your primary aims, which is to image and characterize the subsurface, map aquifer zone, and then to draw implications on surface and groundwater interactions, and to infer the contamination potential of, let's say, your municipal mining and agricultural activity. So in this map, we just show the location of our study area, which was Teresa Mine, which is located in the critical zone. So the area that we were working on was mainly located in the upper critical zone. And then this is just a general map showing the activities that are present there. So you do have like, I'd say this is the mining area. Yeah, this is a mining area. When it comes to district, I'd say the word I did not justify as such because I didn't point out other mines that are in that area. But then we also have like municipal districts. You have your settlement area there and somewhere there, which also I did not highlight, which I should have known to be able to use the word effectively or correctly. And then you have agricultural districts, which are also located around this area, which all as we know, to a certain point, they do pose an effect on your groundwater. So one thing that we looked at while conducting the study, that is in order to understand it properly, was the environment, or I'd say the subsurface in the area. We looked at slopes around the mine. So this first image just shows extensive weathering, which we do acknowledge that some of it is caused by things such as blasting, excavation, and other mining activity that disturb the ground. However, you do see the features, for example, these ones which are more of your tectonic effects or fracturing, which I don't want to call boulder, which I don't want to call beddings, but then just to be safe. But yeah, so this, we do know that some of these fractures, they are formed by activities such as the cooling of the bushveld complex. When it was in place, the load that was in place on the bushveld, which caused it to have some fracture at some point, and many more processes. And then we do see extensive weathering also around the mine, which is not surprising as such, because it is often said that, or it's often found that in the bushveld complex, your weathering can extend to depths as great as 25 meters to 40, 50 meters beneath the subsurface. So yeah, and then this I just included to show the presence of least weathered zones within the what we may call our weathered zone in our area, which is also key to the results that we're going to be showing. Okay, the contrast here is not that great, but then yeah, the techniques that we used are multi-channel analysis, which most people call MASW, and then electrical resistivity tomography. So, as we know, there are a number of seismic waves. These include your body waves, which are your P waves and your S waves, and then you have your surface waves, which are your Rayleigh waves and your lava waves. So this technique, what it focuses on or uses to produce results is it focuses on the dispersive nature of your Rayleigh waves and your lava waves in order to make the near subsurface. So this is just an example of how you process your data. So you get your short gather, and then you convert this short gather. So a short gather is just a recording of your waves that you produce. Let's say in this case, if you're using an impact source, and then you convert this short gather into the phase velocity frequency spectrum. So what normally happens is that your surface waves often consist of more energy than your other waves. So when you're looking at the phase velocity frequency spectrum, you often find that your surface waves, they produce more, or they appear as more dominant as compared to the others. So in this case, this red blue thing that we're observing here is our surface wave. And then assuming that, let's say they were using a vertical impact source, then these surface waves are what you call your Rayleigh waves that they'll be mapping, because when you hammer vertically, you mostly produce Rayleigh waves. And then the next step that follows is you pick this thing either automatically or manually. In most cases, this process is not automated in most software, so you often pick it manually. And then you get this guy, which is just an exact representation of that. And then you convert this thing, or you invert it to obtain what you call your 1D share wave profile. So the key link to this is that you use surface waves, which are your Rayleigh waves, and then you convert them into your share waves, which are your body waves. So this is only possible because your Rayleigh waves mostly consist of share waves, or the most dominant profile is share waves. That's why we're getting that. And then if you produce multiple share waves, or you analyze multiple share waves, you get multiple share wave velocity profiles, which you can then use to obtain a profile that just shows your share wave velocity variation within the area that you are conducting the survey in. So this is a share wave velocity profile, but it's also an indicator of the stiffness within the area that you're working in, or the variation in the stiffness, which can be affected by a lot of things, such as your weathering, and more. And then this image just shows the general acquisition to processing inversion steps. And then this is just one of the equations you use to convert your Rayleigh wave energy to your share waves. Okay, so when you're looking at electrical resistivity tomography, this method is just based on electrical conduction. So what happens is that you inject current using, in most cases, but not always, depending on the type of array that you are using, you inject current into your subsurface, and then you measure your potential at different points. So these are what you call your current electrodes, these two, which correspond to those two. And then you have your potential electrodes. And then the results that you get from here, in order to get your potential, that is, you subtract and you get your potential. So for example, if you look at this is what we call level 1, some may call it your first layer. What happens is that if, let's say, this was 2 meters, and then it gives you this depth, if you conduct your survey and then you keep these parameters, you move your acquisition laterally, you end up getting all these points. And then as you make your spacing wider, there is in order to get level 2, you just increase the spacing of your electrodes and you get that. So this just shows how you build up your tom, which we are going to show. So ground-wise, this is what appears, and the red points in this case are your resistance velocities, which you obtain from your potential results, the configuration that you used, and last point. Okay. So this is just an example of what happens. So in this case, you can see that you have 3 varying layers. So you have a conglomerate layer, a sand layer, and a clay layer. And then if you look at this is just a tomo that shows you this variation. So you have the red or high resistivity zone corresponds to your conglomerates, and then I'd say your green to light bluish, so that corresponds to your sand, and then you have your clays, which corresponds to your dark blue, which are not shown as effectively in this case. But then it shows you just the variation within the subsurface and how you can understand it. So acquisition parameters, I just thought I should just first show an image that just shows a closer look into the area that we were working in. So we did a survey somewhere there at the base of telling them, and we called it site 1, and then there's another one there. And then these are just the images at site 1, how it looked, so that one can understand what was happening. And then, yeah, this was at site 2. So this is just an image showing the layout, the equipment that we used to collect the survey. So what we mainly did was that, for example, if you look at A, when we were collecting our data, so the red corresponds with the yellow cable corresponds with your resistivity layout, and then this thing is moving slow. And then your black one corresponds to your seismic layout. In this case, we had to improvise because we didn't have like a proper lens streamer, which in most cases, when people conduct MASW data or collect it, they use a lens streamer. So when we collected this, we didn't have one. So yeah, we had to improvise. So these are just the parameters that we use to acquire the data. So the one thing that I'll point to in this case, which is of, I'd say, to a certain point, high significance, is your geophone frequency. So normally when you acquiring MASW data, you often use your low frequency geophones, which are most cases your 4.5 hertz geophones. But then in this case, we didn't have such geophones at that time. So we ended up using 14 hertz geophones, which do seem to have did a good job at certain sites, or said a certain site, and then not so good at another, but I'll touch on that. So in this case, I'm just showing the processing or some of the difficulties that we encountered with our data set. So in this case, I'm just showing a short gather, which is A, collected from site 1, and the short gather B, collected from site 2. One thing that we noticed, or let me say this blue box shows you your approximate the location of your significant surface waves. And then one thing to note on the short gather is that at the, I would say the channels that were at the end of the spread, we had a lot of noise, and we also had what we thought were electrical noise, but such noise can also be caused by poor ground coupling and stuff. And then in the second, I think, side, we saw what we noticed as guided waves, which in most cases have very high amplitudes. That's why we're not seeing our surface waves as well. But then this affected our results in the sense that we at some point were to cut down the channels that we were using to acquire the data, which also affects your depth penetration and the low frequencies. And then this is just an example of the dispersion curves that we obtained at the first site. So we can see that at the first site, in order for us to get anything reasonable, we had to cut those last geophones because the signal to noise was too much, to the point that when you transform your data into the phase frequency spectrum, it wasn't good or as good, and you couldn't see them clearly. So we ended up losing a lot of low frequencies. So one thing to know is that when you acquiring data using a hammer, in most cases, you don't expect to get frequencies that are below, let's say 10 or 8 and lower. And then in this case, we didn't get frequencies that were, I'd say, 20 and lower in the first site. This was mainly due to a number of reasons. For example, we suspect the geophones that we use, which are not that good in acquiring low frequencies, the site conditions as well. And then, yeah. So these are just the dispersion curves, what we picked in order to obtain a reflection trauma for that site. And then for our second site, we observed that the dispersion curves were much better. So what we were seeing. And then these high red zones, in most cases, they appeared when we were muting our data set, that is, which causes spectral leakages, and you cutting when you cut your data set, in most cases, especially when you're going to transform it into another domain, you call spectral leakage, which enhances frequencies that other surrounding frequencies. In this case, these were often enhanced, but then they are, I would say, energy varied on the processing. So these are the resistivity results that we obtained at site 1. So what we do see that if you're looking at the resistivities, in most cases, they didn't go above 120. And then considering that we were collecting the data in the Bushveld complex, which consists of igneous rocks, you would expect that if a rock is fresh, it should have at least resistivities of greater than 2,000, 3,000. But then in this case, we see that from surface, so from surface and to about 12 meters, which is what we covered, our resistivities were generally low, which means, okay, let me know. And then if you look at the MASW data, which is shown here at the bottom, it's a similar thing, but then the scale is not showing, that's not shown enough. And then these are results that we obtained at site 2, and also at site 2, we obtained a similar result, if I may say, the resistivities are low. But at the same time, our shear wave velocities are not so high. If you're looking at the depth from 0 to, let's say, about 22 meters, we do see that most of those shear wave velocities fall below the 1,200 millisecond frame, which means that there are also low shear wave velocities. So these are just the interpreted results. I'll show them at the time. So these are we interpreted them as your clay-rich zones. So in the Bushveld complex, you consist of, or in the area that we're working in, you consist of anorthosites or norites, which contain your feldspars and stuff, which when weathered, they break down to form your clays and all that. So considering that the weathering in the Bushveld generally is around 20 to 40 meters, we can see this is a weathered plain. And then you do have these relatively high resistivity zones. But even there, if you look at their resistivities, they are still very low, which means that they are also highly weathered zones. And then the shear wave velocity, the shear wave form at the first site. So if you look at our velocities, we do see that our shear wave velocities, we do see that they don't go above 1,200 meters per second, which for igneous rocks is very low, as you would expect them to consist of shear wave velocities that are greater than 1.5. So we do see that what we are actually mapping here, we're just mapping in the weathered zone, and then we are resolving, let's say, least weathered zones within the overburden and the semi-weathered zone. But to that depth that we've covered, it's all weathered rock. So a similar thing in this case, so I won't dwell much on it. And then this profile, we did get better dispersion curves, which meant that we got greater depth. So if we look at the variation in our velocities, the blues fall around, I would say, 600 meters per second, which also classifies it as a low shear wave zone, or let's say a low stiffness zone. And then as you go deeper, you do see that it starts increasing. So we did have one borehole in our area, which we tried to use to constrain the results that we obtained. So if you look at the borehole, you do see that from 0 to roughly 9 meters, you get overburden, which to a certain point corresponds with what we are seeing here, because from 0 to about 10, 9, you do see that the shear wave velocity zones are too low. And then you have that other zone which corresponds with the norite and the melanorite. So we interpret this as your semi-weathered zone. And then that is your, I'd say your least weathered zone in this case, because if you're looking at the results, all of them, they are not that high, the shear wave velocities. So what we then tried to do was to compute models that just describe the type of, or the environment in general. So I'm only going to jump to these last two images in this case. So the conceptual model, we mainly generated them based on the shear wave velocity results, which give you the variation in your stiffness, or to a certain point, you can say your weathering within the study area. So in this case, we do see that we have overburden, which covers like the first 10 meters, but then laterally, you also see that the depth of that overburden varies. So from one point to another, it can change. And then you have your semi-weathered zone there, a similar thing in this case. And then this is just a borehole, so that someone can look at the interpretation and try and make sense of it. So in this case, our general findings, so the first thing was that we observed that the presence of low resistivity, then shear wave velocities in the top 20 meters, which mainly indicated that we were mapping on weathered rock, which we suspect in this case forms part of the near surface weathered aquifer. And then we also observed low overburden protective competence. So what happens when you're looking at the competency in results, or in terms of the images, if there was a high overburden competency, you'd expect to see high resistivities in the top layers, you'd expect to see high resistivities in the top layers, high resistivity and shear wave velocities in your top layers. So in the absence of this just suggests that there is a presence of soft near surface sediments such as clays in the bushveld. We know that it consists of black clays, which they do absorb water, but at the same time they are very porous. And then we have fracture zones, which in the conceptual models we did not focus on because our resolution scale, I would say, was not that high for us to make them a main concept, if I may say. And then this, what they suggest is high surface and groundwater mixing, high hydraulic conductivity as well. Okay, the last point is deep weathering. We observe that there's deep weathering, which, as I said, is expected considering that the range that is often found for weathering varies from 25 to like 40 meters, 50 meters. And then these are just conceptual models that we created to describe the environment. So the first image, which is your first one, just shows the general variation within that. Oh, it's not off on the, sorry, it's off on the piece is off. So in this case, what you observe is that it just shows the general variation, which is your overburden zone, your semi-weathered zone, and then your fractured rock. And then the second one just shows the least weathered zones, or presence of least weathered zones within the overburden. And then the third one also shows, which is C, shows least weathered zones within the semi-weathered zone. And then the last image, which is D, it shows possible leachate migration paths. So considering that the bushveld consists of a lot of fractures and it also has near surface aquifers, this means that the water in the bushveld, one, is not protected, and then secondly, it can be easily contaminated, saying that there ought to be a leakage of some sort. So in conclusion, We observed low overburden protective competency and inferred higher hydraulic connectivity in the region, which suggests. So assuming that the subsurface characteristics observed along these lines at the Teresa mine are representative of subsurface features in the nearby agricultural, municipal, and mining areas or your industrial areas. This does mean that your weather zones are vulnerable to contamination by mining, agricultural, and industrial activity. And then possible contamination sources include your industrial influence, acid mine drainage, urban and agricultural runoff. Thank you.
Thank you very much, Camilla. Any people? Want to talk? Do you know if the mine is going to take this data into account or?
The one that we collected? I don't think so. So when we were at Teresa mine, one of the things that we did, especially in this case study, this was like our first time as FEDS collecting MASW data. So we collected some data just so that we could learn about the technique, and this was one of the data sets. And then the ones that the mine are using, there's another case study, which unfortunately, as I said, my talk, I knew it was going to be long, so I decided to exclude that. But most of the stuff that are there, we collected resistivity data, collected MEG data, seismic, and then today, in fact, looked at isotope data, which those are the data sets that they are going to be considering, but not this one. From my understanding, that is.
Okay, okay, let's get started so we can finish on time. Thank you very much.
Thank you so much.
Trond is up next, but from what I understand, Lou is gonna. I'll get your talker. This one here.
Okay. Got it going.
Oh, wait, let's get your pointer, which should be over there.
Pointer. Do it, just do it.
Trond is amazing. Yes, supported a lot at the university. Thank you for all your time and efforts. Thank you.
All right, last one to go. Thank God. So I've known 28 years because that's when I started coming here, 1995. So I've known her for almost half her life. And she doesn't look a day older. I've given endless talks there. And I changed subject every 5 years. First came out, it was interesting in the Precambrian. We went to Madagascar, India, we worked in the Rodinia supercontinent. And we switched to various other things. I'll say more about it in a second. So now we changed the game. So we come from the Central Evolution Dynamics, which ended a month ago. So that was the end. For 10 years, it's called a Central Excellence, where we spent about, I don't know, 500 million rand or something ridiculous. I don't know, a lot of money or less. So that's over, but we want a new center. It's called Center for Planetary Habitability, another 10 years, and that will bring me to 76. So that will be the last one. I'm involved with Stephanie Werner, who talked yesterday. We'll take care of that when I retire. And this is just a pic. We had a, how do I move this thing? An arrow? Or space? Ah, so we had a conference, and you can see in the middle there is Sue and Lou and Stephanie. So we had a big conference. So this was the seed from 2013, 2023. So we had a big conference and where we summed up everything we achieved or not achieved or whatever. I think we achieved a lot. Not everyone agreed on that, but That's why science is to argue about things. So this is just what the old center was about. So when I first started coming here, I was very much in the dynamic, making paleography, reconstruction, and so forth. But after some years, I got interested, for instance, in large igneous provinces, lips. Where did they come from? So we developed this theory. They came from the Cornell boundary around this sunny last low levels to provinces. We also postulate they've been stable for a long time, maybe hundreds of million years, maybe billions of years. Not everyone agree on that, but haven't got any convincing counter arguments to be true over 10 years. So I'm sure people would spend more effort, but we are left there. We also, in 2010, we also switched to kimberlites and diamonds. We had a native paper in 2010. That's also where Sue was on. And we also had a lot of effort on Earth cry, systematic extinction with lips and so forth. So that was our old life. And the new life now is this Center for Planetary Habitability. You can see it there. This is actually the third center in a row of these 10-year excellence, which I've been involved in. And I was originally not keen on doing another one. So I said, if we're going to win another one, it has to be so extravagantly crazy and ambitious that it will be funded. And it got funded. We were rated very high. So the objective recognizes and characterizes the key conditions that make the planet habitable. So that's it. This is the day we were told in the morning we won it. So that's another 300-400 million rand, start pocket money to get going. But what I'm going to talk about today is not, Stephanie talked about, so I kind of three teams. What is modern Earth? Modern Earth is the last 750 million years, and early Earth. And then we also have exo-Earth, which is Stephanie. But of course, we have to build what I'll talk about now. I'll talk about Earth, because if you have to know what to look for. The problem, many times, the people who actually, astronomers, try to look for Earth-like objects, have no clue about our own Earth. Okay? This is well known. So we are doing this all in one sentence. We have to understand our own planet. We don't really do that either. So that's why I'm saying in-depth knowledge of Earth-like habitability, how our own planet sustain condition for life's evolution of the logical timescale is critical for identifying habitable planets. If you don't know anything about our own Earth, particularly the early Earth, you have no clue what to look for. You can have all these, whatever, there are 5,000 to 6,000 of these objects now potentially described as Earth-like or habitable. So you can always rephrase our objective to what makes Earth unique, because we are unique. We're the only planet in the solar system which has life as we know it. Maybe you find a bacteria buried on Mars. That would be it. Even our solar system might be unique. Be aware of that as well. We haven't seen actually other star planet systems even looks like ours. So Earth is unique. Our solar system is unique. So we have to understand that before we go on. And this is just some diagrams to make the point in our application how unique Earth is. And there are some, we'll come back when you define kind of the initial condition to define planetary habitability. Actually, you need surface water. Okay, so Earth is among the rocky planets with abundant surface water, which I didn't know when I started. I was quite trustee. Of course, I've known about the moon since I was a kid, but I wasn't aware we're the only one with a large satellite or moon of these terrestrials. And I never thought about is that important or not? So that's something to look into. Yes, magnetic field, that's where I come from, but I also knew that, okay, Mars might probably had it in the beginning, Mercury doesn't have it, Venus doesn't have it. But a long-lived, that's the key here, the long-lived, because on Mars it stopped, maybe at 3.7 billion. So we have a long-lived magnetic. Now we have plate tectonics, unique, maybe the most important to regulate climate. So Earth has all these ingredients, where we have an atmosphere, we have a climate, we have light, we have water, and we have this interior process. And if you then compare it with the other one, no dynamo, it turned out maybe we're the only one with a solid inner core. I thought Mars, when it had a magnetic field and the inner core starting to grow, and then it filled the whole core, and then the magnetic field stopped. And we learned That's probably utterly nonsense. Now people, although based on one seismic or mass claim, there is no inner solid core. So then we have to rethink that as well. So, and no shear velocity provinces, no life, probably no core convection, stagnant lid, the dry surface. So we have to understand to the left why we're unique. So planetary abilities, this is very complex. There are so many things you have to think about: atmospheric composition, surface tectonic style, water mass, magnetic field. You have all these things. It's a wide range, but the most important, which makes it even more complicated, is that they're all time dependent. Okay, things change all the time. So that's the real, to understand habitability, you have to understand this time dependence. Otherwise, you're in trouble. We know from Earth, we started off 4.5 billion years ago. It's sort of molten mass, and we had the moon forming event maybe 50 million years afterwards. People talk about a snowball. Earth for the last 600 million years or so. So it's this time dependent. It's very, very important. And Stephanie showed this diagram. Planetary bills commonly defined by the presence of liquid surface, and we've drawn this blue envelope here. So today Earth is sitting perfectly in that habitable zone. But that's with an atmosphere of today, but actually very low greenhouse gases, CO2 only 400 ppm or 0.04%. But of course, and then Stephanie said, when you go back in time, this kind of analysis become trouble because Earth seems to be too far out because the sun is only 70%, it's 20% weaker. So, and of course, that has troubled people for decades. How did we? And then there's another explanation for that. But the point is, the Earth-Sun distance, when it all started, we were not optimal. So Earth would have been too cold, as I said already, not faint sun. And but some of the things, what saved us from runaway cruising in a permanent ice house, like Mars became about 3.7 billion. But not only that, what maintained habitability when life started kicking. Because we know the oldest fossils, bacteria go back to about 3.5 billion. Yes, some people dream that life might even started before 4 billion years. So if it did, what managed to maintain and made us be able to sit here and talk to each other, it's almost a miracle to think how Earth started in the wrong position. And Stephanie hinted to that because the secondary atmosphere is what saved us. This is degassing from the magma ocean. And although we argue how much CO2 you actually had, but typically numbers people talk about 70, 80% CO2. And maybe a lot of methane. And you know, you probably heard about for something we talk about climate sensitivity. For each doubling of CO2, the temperature goes up a certain, we talk about 5-6 degrees. So this would be enough to compensate for a much fainter. But of course, this degassing is slowly going down. And you can see here at about 2.5 billion years, we think it maybe was down to 5-15%, maybe even lower. But then you see Earth now, starting outside the habitability zone, there's no crossing in. So now we can afford to have much less greenhouse gas in the atmosphere. So the sun is, because the sun is steadily increasing, and we are losing that amount of CO2 2 times. So CO2 saved us, okay? We talk about global warming, climate change, CO2 is going to kill us. That saved us. Without that amount of CO2, I would not been able to talk to you, okay? We would have been dead planet. We would have been Mars, maybe I said. So that's how it is. And of course, the third atmosphere, Stephanie showed it so well. We have this great oxidation event. And I like to point out to when I teach this for students, it's about 1%. So that's why they plotted on a logarithmic scale, because then you can see one. Plotted on a linear scale, you don't see one. You know. So this is very important. We have a lot of ideas why this is cyanobacteria, produce over a certain threshold, but something promoted. We have ideas about that. But what I don't really understand is what they call a near-Earth observation event, which came from about 600 million years, when we started getting CO2 levels, around our levels. That one is actually very little understood. And remember, oxygen is models. You cannot measure oxygen in time. These are all models, okay? And okay, so now what I'm going to talk about, there's a lot of parameters. We understand Earth and how it's changed. There's all these environmental drivers. And I plotted here from those who are very, very slow, like changes in the sun strength, come back to changing the length of the day. And of course, we have impacts. So this goes from slow to fast, okay? And then they all come dependent. And some of them are truly unique to Earth. The yellow one, changing the length of the day. It's sort of partially, but you see plate tectonics, we don't know about any other planets. Change the magnetic field, we don't, because they don't have a magnetic field, so we don't have to worry about it. Since we don't have advanced life, we don't have to worry about Anthropocene trouble on Mars or Venus. Okay? But a number of these you can find on others. Something we call true polar wonder. They are on them, and of course, the orbital parameter. So I will talk about some of these, because we have to understand all this and how they work together to understand why Earth has been able. So the change in the sun strength is one of the most important. And as Stephanie pointed out, in the future, but luckily in 2 billion years, whether you're afraid of global change or whatever, this planet will be non-inhabitable, okay? In about 2 million years, it would be so hot that the ocean would evaporate, okay? So that's the end, but we will not be around to see that. And also in carbon cycle modeling, we have to take into account the change in the sun in the past. It's almost on a linear change for the last 700-800 million. I just made it almost linear back to 1 billion. You can get an idea. If you go back to 500 million years, within the early Paleozoic, if everything else was stable on this planet, there should have been a 7 degrees increase in the surface temperature. Okay? If nothing else changed. But luckily, a number of other things did change. Like we've got plants and trees with increased weathering and the cooling, but there are not going to be that many tricks in the future who's going to account for the steadily sun will take us out. And so that's important. The moon, which I told you to really bother the moon, I saw it every day or on a clear night. So people think maybe it formed some 50 to 100 million years after, and you had some sort of Mars object to hit it. And at one point here, it led to a very fast spinning Earth. Maybe one day, it was only 3 hours we talk about, it's slowing down. 3 hours, you didn't have time to go to bed before you had to go up if you lived on the planet. So it would probably not be a very habitable scenario. It definitely kept Earth probably quite uninhabitable for some time after the moon forming event. So, so this is just some scenario. If you woke up in the Hadean, which means hell, in 4 billion years, you would see the moon was almost close to it because it's slowly going north. So it was very close. And we can also about to about 500 or a little more, you can see on a planet when it goes slower and slower is that the tropical belt, which is the warm, wet, where the most weathering is most intensive, this belt is slightly expanding. So the sun is, for instance, getting warmer, but this can actually counter it a little because you're actually increasing the belt, which can produce more weathering and more cooling. So that's something we can do some calculations. And Of course, the Milankovitch has 3 different cycles, but the one the moon control is the tilt, which changes a little. And the further, and it used to be smaller. Some people have written papers about if the moon is too way out, well, then the tilt be totally unstable, and kind of civilizations live on the planet who actually where it's tilting all the time and how fast. Others are saying, don't be worried. But the tilt. Of course, the magnetic field is something I work on, but I'm the most important, I'm really the only one with a long lived. And and of course, it protects us from cosmic and solar radiation. And also they're saying that when the magnetic field stops, some will claim that the solar wind would blow off the atmosphere. Some say that's maybe not. I think that happened on Mars, but on Earth with a bigger mass, it might take 1 billion years if the magnetic field stopped tomorrow. So we don't have to worry about it in the short term. And of course, there are countless organisms and species that use the magnetic field, and it can affect climate as well. So, but it's important that we are the only one with a long lived. Mars definitely had it, but it was gone quite early. So I talk about plate tectonics, since that's where I really come from. So it has a number of effects. It regulates interior temperature. For instance, on subductions, you get a recycling of various volatiles, and it's probably essential for sustaining compatibility. Maybe you need it as a driving motor for the plates themselves. You need this sort of volatiles going into that. We also know that the sea level was probably much higher in the good old days because water is slowly sinking into the mantle. Some of it is returned back, but there's a net. So some people are talking about maybe there is 1 or 2 or 3 oceans in the mantle. If that's true, then the sea level must have been much higher during early Earth. So that's one thing. What I've been involved in the last few years is more that it regulates greenhouse gas and therefore surface temperature via sources. You can have that on, so here you have a subduction, you have some sort of Andean margin here, and you have volcanoes, you have active sources of volcanic CO2 degassing. So that's important, that would bring it warmer. And then you have sinks like the silica weathering and carbonate deposition in the atmosphere. As long as this get deposited, you make the carbonate, you will have a net losses in CO2 and you will cool the climate. And I made a joke the other day. I wrote a proposal on this. I wanted to get a big grant, but I said I don't want to get into silica weathering. How on earth do you quantify that? And that hit on me. So now I spent the last few years actually trying to understand how you do. So I had a PhD student working on it. But there's another problem with plate tectonics. So we have some number of these, how this can regulate the climate. The main trouble is, when did it start? We haven't agreed on when plate tectonics started. So it started with this enormous degassing from magma ocean, and you had a CO2 dominated atmosphere. It was kind of slowly decaying, and then plate tectonics kicked in at some time. But when? Jesus, we don't know. Any number goes from more. So that's the oldest part we call a Hadean, and the youngest in the Paleozoic. You can read modern literature. Some people say, ooh, this happened almost at day 1. Mark Harrison is a lover of that. Happened very early. And then you have other people like Mike Stern saying, hey, wait a minute. Maybe it only happened at 700-800 million years ago, because he's pointing out that Bluetooth metamorphism, which doesn't come into existence. And so steep cold subduction, he claims, is when you see it. It's so young. So, and we don't know how and when we go from an earlier king. And this was a water world. I said the sea level might be much higher. We hardly have any continents, Okay, there was thinking before, when we think about continents, we think about granites and stuff like that. And you had to make this stuff. And there was probably very little of it in the beginning. So, so this is things we have to try to understand. And just some ideas which I try to follow. You had some sort of stagnant lid almost like some of the dead planets in the beginning. I would at least guess plate tectonic started in some form, maybe about 3.5 billion, but the mantle was much warmer, so that it would be hard to subduct material, and the subduction would be much more shallow and not steep. So it was a very different scenario. We know also from Paleomag and the we start plate tectonics must have operated in some form, because it looks like you're gathering some cratons together. So there must be some horizontal thing. But they are not very big. This is one of the, we have these 3 types there. And I show you one of this superior, and you have Kapval plate on here, a part of Australia. This was one of these, but it's quite tiny. And it was about 17% of Pangaea, which means all land, the youngest. So that's about the size of these things. And if you come to Rodinia, which I used to work with, also with Lou, you have about 70%. But that's the problem. We cannot reconstruct all the plates, or maybe they're deformed too much. So we have a problem identifying these things through time. So we have this Rodinia there. And then Gondwana, and if you believe, for instance, that modern plate tectonic with cold steep subduction started very young, well, then you have a scenario. Maybe Gondwana was the first. And now it's also interesting, because I never used to call it supercontinent, because in the literature, we don't call it supercontinent. It's called a superterrain. Kevin Burke hated it. He said it was this one and Pangaea, the only one we know about, and all these old ones are some romantic nonsense, because we have so little data for these Precambrian ones. And in my next paper, I will actually go back and I will call it a supercontinent. And it makes a lot of trouble for people who works with this, because people have decided there is a cyclicity in supercontinent. You see how you have this thing, and Luna, Rodinia, Pangaea, they go in at like 5, 6, 7 million years. So people write papers on cyclicity. If you now say Gondwana was a supercontinent, you kill all the models, because suddenly you have this thing in between there. And so that's why people are not happy that we call this a supercontinent. But this is maybe what it looks like about 500 million years ago. So there's the South Pole, this is in the Cambrian, and of course we are down here. So, and this is just of Pangaea. This is the youngest and best known supercontinent. So, and I'm not going to, and of course, this was what I used to make my living, making this geography. I was plotting the thing, plotting shallow shelf and dry land as well. But I'm not going to do that here. I'm going to use it now. I'm going to use my paleography background to first show you how you can figure out global weathering, which is a cooling agency in the plate tectonic. So how can we, global weathering is, so how can these be, sinks and sources be defined? Okay. We know when we look at Earth today that, okay, we call it the tropics. The word tropics simply comes from the tilt of the 23.5 degrees. So everything which is in there is called the tropics. But we know the most intensive weathering, the warm and wet, is within 10 degrees from the equator. It's undulating, but roughly 10 degrees. So that's how we can quantify. So we can run these reconstructions, and then we just have to measure up how much land. But it's more complicated, because if all the land were underwater, it doesn't matter. We then have to figure out what is real land and what is shallow. So we need that. So here is some of the maps, for instance. This is a new one for the Silurian, where you can see what is land and now, and because we normalize that today, we know how much land we have today, and then we can normalize. And we also know how much land we have in that 10-degree belt, so we normalize everything. And we can make some reconstructions, and then we make it. This thing here, how can I get rid of this? Huh? Ah. Yeah, but I'm afraid now I'm going to click them. Huh? To the side. Whatever. No, but here you see from 0 to 700 million years, we've only done this to about 540. If you figure out how much And land you have in this warm and wet out today, which is exposed. So then you have to count for sea level change. Then you normalize it back in time. So 1 is today. Then you see it was much less in this period in the Triassic, Jurassic, Cretaceous, when we know which was warm period. So if it's not wet than today, you have less weathering. Okay? So then it keeps it cool. And then you can see here around Pangea time, it was back to about what it was then time. And you see here in the late Ordovician, you have lots of them there. So that would increase the weathering. So this is a very simple thing we're doing now. So now we globalize this, simple as this.
Click on the spot.
Okay. So turn out, if you look at, now I can't see because it's supposed to be green. You see cold ice after. It turned out we live in an ice volcano. For the last 500 million years, there have been 3 ice caps. A very short one in the late Ordovician, maybe only 1 million years. And this is about that time. And the longest we know started about, it's defined from 330 to about 260, but there were also glaciation in the later on early Carboniferous, so like bring it further on. But you can see there the amount of silica weathering is about like today. But remember, for the last 30 million, we live in an ice cap. So we live in a warm period of an ice cap. So we actually live in an ice. So ice are going to present day have higher weathering rates, and they see there's some sort of roughly when you have an ice house, not a snowball Earth, that you have reasonably high weathering rates. You're above 1, and then you can see when you're below here, we also where 90% of Earth's history, Earth has been a greenhouse. Okay, so when we talk about global change and all this thing, remember we live in an ice house, which is quite unique. There's only like 10, 12 of them in the entire Earth history. But we, the civilization, involved. Now we can look at, so we can get some handle on weathering and cooling, the sinks. We also get some handling on the so the plate tectonic, the most important is on subduction sound or Andean types. And what do? We make plate models now, real plate tectonics, where, of course, we have to make them up. You're aware of that. We make up a lot. So that, right? Now it's kind of a computing game. And we have a software called G-plates, and people take it very seriously. They do all this calculation. I'll show you. Be careful, but that's what we do. So we make up all these things. Not all of them. Along the continents, we have a good guess that there was a subduction sound, but then we make need a spreading somewhere in the middle of the ocean between them, and of course we make it up. Anyway, when you make up all this, then we sum up subduction flux. So we have the length and we have velocities. So we get a number today again. Now we're going to normalize it. What is the plate tectonic activity today? And it's actually very low. So that's 1. So you see, if you look for the last 70 million years, we have the lowest. We're in a very low plate tectonic regime. And you see, when you go back here in the Cretaceous, it was about 2.4 times higher. And you can see various things. You see where I trust it the most is actually this red curve here. When you go to the stipple one, I will tell you where it comes from. You can really only trust these things shortly before Pangea, because we make up more and more when we go back in time. Remember the oceanic crust on the oldest is 20 million years. So before 20 million years, we made up the entire oceanic crust. Okay? It's purely syntactic. Doesn't stop us from doing calculations and write a lot of funny papers. But again, if you're going to believe this, ice are linked to low degassing rates. So you have low degassing, but I told you earlier, there's some sort of semi-correspond to high weathering, which is a sink. So maybe it's this time you have low degassing, sourcing, and you have high weathering, which is the cooling. And that's when you have these jointly working, that's when we get, you cannot see these blue bands on the ice. So this is kind of a simplistic way. Others have different opinions. It's a very black and white discussion. Because people who works with weathering are saying it's all controlled by weathering and cooling. And people who works with plate tectonic degassing, they say it's all caused by that. So maybe if we all got together and talk to each other, maybe we'd make some sense out of all this. Just show you, with all that, we can do something we call carbon cycle modeling. I'll show you here, this is from 0 to 8,000 ppm. Remember, today it's about 410, but you know, before humans start playing with it, it was about 280 ppm. That's kind of the background. It's very close to the mean for the last 30 million years. We live in an ice house, so it's quite low. And now, in this blue line is the last ice house. You can see from this modeling now that it's there. And then we have this very short-lived at about 445. And then there are some others back here, but now we're getting into a little fantasy. And this thing I will kind of believe in this way. We also have an idea about temperatures, but again, you cannot map the temperature in the Permian. These are models. Well, from shells of animals, you can do look at oxyisotopes, but it's not just measuring the oxygen isotope. There's a huge formula and all this thing you're going to take as the seawater being constant or not, and you can end up with a lot of different temperatures. Be aware of that. And what it looks like, and I kind of believe that it's quite high in the Lake Cambrian Early Division, but if you look from about 450, the temperature has been pretty similar. There are oscillations. It's lower during ice out. So despite the sun has increased 7.5 degrees, temperatures are oscillating. And there is no big trend here. You had this big fall here. So what do I see? Reduced plate tectonic. So what we think is responsible for this thing, here I now put on plate tectonic degassing and I have weathering. You can see there's a reduction here, which seems to kind of correspond to the ice houses. But also when you see the weathering, you see that the weathering is more cooling, so it's working together. That probably can explain why we have these ice houses. So it's a combined icing. But I've only worked with this for about 3 years, and we have another 10 years. But there are other things there, you know, because we heard yesterday as well, we are also getting plants and then big trees for the later ones. And of course, these are also good to reduce the CO2 level. That might, and for instance, in this model here, you can see a large reduction here in the CO2. So that's also important. So it's another parameter. We do this also plants before, but then we didn't have roots, and these are also incorporated into this software. So this is a lot of stuff to show how reliable are these plate tectonic. So this is the red one, and I don't really believe it at 500. I would believe it at about 350. I had another postdoc who extended it, but he never published it. And if I had another postdoc, it would look different, just to warn you. And then, of course, there are other people doing the same. But first, I have to show. So what we decided, okay, if we can only do this in some reliable way back to 300 or whatever, we have a circum database, you know, with 900,000 observations. And most circums are in convergent environments where we have the subduction flow. And in one of these databases, actually not related, you can actually take out an environment which they think were related to subduction. Okay. And then you have the problem, you know, there might be 10 samples from Africa and 1 million in New York State. So you actually have to start, you have to start to balance out this. You have to do an area scaling to make sense of it. Otherwise, you will get big peaks wherever people have a lot of data. So it's a lot of things. And of course, the problem, we normalize everything to 1. That's the problem with circles because, okay, we have subduction today, but the circles today hasn't been produced yet, okay? Because now you're going to maybe make a granite and then you lift it up and on the road, there will be 20, 30 million delay. So you cannot take today. So you have to forget that. But what I've done now is to take all the peaks. These are circum peaks and lows And I actually fitted it from here to there. And then we just force it to go to 1 because we don't know what 1 is. Because that's in the future. We cannot hang around to see what that value is going to be in 20 years' time. But anyway, we can get a reasonably correlation. But the good thing with the circum curves, they go back to 4 billion years. So then I can go all the way back if I think this is a reasonably estimated. And now I'm going to show you a curve by some Australians, because they think they don't play tectonic modeling back to 1 billion years, even though I think it's a computer game. You don't really know. It doesn't stop people doing this. So they made a model to 1 billion, and they've been on all kind of media. Now we understand Earth for 1 billion years. You can see, so that's the green curve. You can see here, there are gross similarities, but as soon as you now go beyond 300-400, the green curve is down here and our estimated there. So it's a factor 2.5. Okay? So you kind of trust these things. And our model doesn't go back. So I took the latest model by another group in Australia, Perth, because we have a better model than the Sydney. So let me show you their model. And that's the other. Now you can see, so you can look here how different things can be. 700, this is there and this is there, you know. So, you know, if you use one of them, the Earth would be hell house, greenhouse, or it would be hell, you know. So that's what I'm telling you. You have to be very careful. And so grossly similar, maybe 350 before that time, you not trust any geodynamic calculation, whether it's plate speed or this and that. So we prefer to normalize that to circle, because it's the only objective in some way. It's the only way, in some sort of objective way. And the other are computer games. Okay, so be aware of that. I'm not going to dwell on this, but all the stuff we're going to work in the center, not only understand the plate tectonic, we also work with other people who are now coming up with potential natural temperatures over the whole time as well. But these are also modern models. We now think it's about 1380, but maybe at the end it was about 1700. This is a 200-kilometer depth in the mantle. It's showing how the mantle is cooling. We're also working with people. Why do we have this long-lived magnetic field? And one idea is that it's slowly decaying, it's fluctuating through time. And if you don't get an inner core growth, it will stop. And this is a very dramatic model because there's no model here to this big thing. And when you go to inner core, we also know I'm normally a big fan of pattern intensity because even in the Cretaceous superprime, you know, 40 minutes, I want to know was it high or low, and they tell me, wow, depends on which method and which lab. The only good thing here at about 600, whoever does it seems to get probably any field. It's almost gone, maybe not to 5%. So it looks like the dynamo almost stopped. And if you look at parametric data, nobody can make sense of it. You cannot make reconstructions because the Baltic, that would be probably in the wrong place. North America would, on the equator, it should be another. It's chaos. I call it chaotic. It could be. So that's the working. The other thing, so if we use the circum record now, I show you where this peak. We can actually now maybe quantify relative today for all the way back between a billion years. But that also depends when did plate tectonics start? When are these curves applicable? So there's a lot. And we can do weatherability. I've extended that to 2.5 billion. And we also playing models. I'll show you carbon cycle modeling here, and I try to combine everything there is in the literature through time, now here to about 2.5. Just kind of a brief sum. If you look at what we know about Earth, we probably had ocean and dynamo very early. Life might start at about 4 billion. You know, the cyanobacteria, which is photosynthesis, can produce this oxygen, which make us talk to each other. So I'm not a big fan of bacteria. They've done a lot to my bodily harm to my body, but without them, we wouldn't be here. Okay? They produced oxygen. Oxygen didn't come out of a volcano. Okay? And I also said, here you can see now, when did we have the ice houses or snowball Earths? And you can see, I told you Earth is basically a greenhouse, and you can see the first actually known When we have glaciation, it's about 3.5 billion, and that's from Southern Africa. Martin de Wit and Harold Fern wrote about it. Because it was this idea, even though it was outside, they had some stable ice tops. So it's very high temperature, and Martin de Wit and say, hello, we have glaciations. So it can't be, 70, 80 degrees surface temperature all over the planet. So I will tell you, maybe it's a snowball earth. But anyway, greenhouse effect, a dozen ice house, two periods for maybe snowball earths. First known ice house, 3.5 billion, that's Martin de Wit. Older snowball earth, 2.4 billion. And Mars were then a permanent ice house, and Venus was a hot house. She showed that already, so it was only Earth to think about at that time. So there, the first snowball earth. So that's not. I originally didn't believe a word about snowball earth, but after listening to Paul Hoffman, and this time I gave up because he had so many arguments. I said, you could have convinced my dead grandmother you're right, because he has a lot of things coming in there, but I think we still don't understand the mechanism. I don't think he knows that either, because it's kind of a word. They call it some sort of, mostly think that it was some extreme cooling by Webb, that you had a large igneous province erupted in that 10-degree belt where it was warm and wet, and it kind of was so wet at 10 times faster than the ground. So you've got some catastrophic runaway cooling, but it's a lot of word salad to me, I think. Okay, so I don't think we really know. So the last and longest snowball earth, which Paul also worked with, was about 720 to 640. Some student asked, can we get another one? I don't think so. Remember, the sun is steadily increasing. The plants and trees help us a little to compensate for that, another thing. But the Earth's not going to pull more tricks out of its pockets. So I don't think we will go to another super cold period. So that's the last one there. So, and also I said the largest known house, really well documented, about 330, 260. It could have been older, could be probably starting the late morning. And we live in one, that's important. We live in an ice house, okay? So we live in an unusual time. We are unusual creatures. And I'd say ice house snowball are mostly linked to low atmospheric and reduce, but also reduced plate tectonic degassing. That's what we can see. So I've shown you this before. We can mostly correlate these two. And yeah, so here is this plate tectonic degas. So, and I put a question mark here. Now it's interesting. Snowball earth. We have very little there. So the second one there is partly based from South Africa. It's one. And then they've done Halimag and some lava, I think they're above. And then they got very low latitude. So they have one measurement, say snowball earth. Okay? That's why I thought this is crazy. But it's not that crazy, because if you really have an ice on the equator, it doesn't matter, it's enough with one. Unless it's a high alpine one. But if it's really something which is carving into the sea and they claim it is, it doesn't matter. One is enough. Well, then you can also go back to Martin de Wit's first one, because the Kalahari or Katwal or whatever, that glaciation was also literally on the equator. So then you can actually write a paper. Feel free. Snowball earth, because it's equally less convincing. It's one observation. Okay? But you only need one if you find some glacier on the equator, because it shouldn't be there, unless it's some higher altitude thing. So we have to figure that out. So we're going to look into how oxygen, and now it's on the log scale, so you can see the big change in oxygen here. Methane, this is also a model, but it must have dropped dramatically, because methane is a very efficient greenhouse gas. But as soon as you put oxygen in the atmosphere, it will oxidize. So if there was a lot of methane, it would really reduce. And that, I think, is a clue to understand the first snowball earth in terms of runaway cooling. If you had a lot of methane, oxygen, you took it all out overnight, that would could have led to a runaway. So it's not a weathering. So that's something we will look into. And I kind of talked about most of these. I don't care about it. So I was a little faster. Doesn't matter. So we have some idea about its atmosphere. So when Stephanie and her groups come to look for other, we have to look for the spectra. And if you were imaging Earth, you show this one, you will see water and CO2. And if you are looking at the third atmosphere, you will see ozone, which means you have oxygen in the atmosphere. This is what you want. So you want to find that on one of these objects, which goes around another star. And if you do, just to inspire all the young people, if you are on that mission, finding that spectra, I can guarantee you we get a Nobel Prize. Guaranteed. Be aware, the first one who talked about and discovered, oh, we think this is an Earth-like, there's another one, they got a Nobel Prize. Okay? Well, if you find that spectra and everything else, you know, the age, whatever, Nobel Prize. Yeah, we have to share it with them, so you can get $1 million each, but it's always nice to have at home. So now it's almost ending. Okay, so now we think we know something about plate tectonic degassing. I normal that today, but we can actually give you a number. How much is this in CO in gigaton per year? Because we are worried, Anthropocene. People talk about we produce maybe 50 gigaton of CO2 per year. Yeah. Can you ever find that in the geological record? And the answer is no, unless you go to large igneous, catastrophic event. So if you go back to 17, you see, so now we have in gigaton CO2 here, and you see what from 1850 and so forth, it has been going to the roof. I didn't put on here, if you take also the growth rate of people on the planet, you can fit that equally well to that. Because it doesn't matter if we were constant 200 people, you know, just inventing all these things, that's what happen. The problem is we also get more and more people doing this. So you can literally, the population growth curve can literally fit this one as well. But look at this. So this one goes to maybe 50 gigaton. And here I show you this blue line here is present day plate tectonic degassing. It's about 0.5 gigaton. So now I think you got to think plate tectonic degassing natural per year is about 0.5 gigaton. And we humans make 50. So that's a number that we worry about. Okay. And I'll show you the highest we have figured out is in the Cretaceous, is to here. It would be about 1.5 gigatons. So we are way up. Okay. So this is the worry. I also probably show sea level, because sea level is actually the other way around. We're worried about sea level rain, but sea level change, natural processes can be as much as 5 centimeters per year. And we are doing millimeters. So that's a totally different game. People should not have populated these low areas right now. So that's the end, not for the world, but for the lecture. Yeah. All right, and then I need a drink.
Not too many questions.
Yeah.
Any questions?
No.
Go and get a drink.
Yeah.
Ask him a question over a drink.
Yes. And on Saturday we will meet many of you as well. Yes. We will meet many on Saturday.
Thank you.
Yeah.
Thank you, Sue, for turning it.
Yeah.
And I have a good evening, everyone, and a good volunteer, and have a for that January. Thank you.